And we will, we are recording. Let's get the slideshow going from the current slide. Sorry about this, folks. All right. Now, before we get started on the physics today, or physical science today, let's talk about how the term is winding up. Okay? Today, we'll definitely, knock on wood, finish Chapter 6. We'll start Chapter 8. We should get a fair going on Chapter 8. It's not a super long chapter, but it's fairly intense, involved. So we'll get a good start to it. Then the last 2 hours today, we'll have the last lab on Chapter 6. Electromagnetism, okay? And then Thursday, we may finish Chapter 8, or may not, but I think we'll get far enough along to at least have the lab on Chapter 8. Well, we're only going to have 2 hours of class, so we may not finish Chapter 8. Then we'll do 2 hours of lab on Chapter 8. I think we'll be far enough along in that. Then we'll have the last 30 minutes, the test on Chapter 6. That will be Thursday. Next Tuesday, if we didn't finish Chapter 8, we'll finish Chapter 8. Or if we finish Chapter 8 on Thursday but didn't have time for the lab, then we'll have the lab on Chapter 8. But we'll have something going on there, and that's next Tuesday. And then what I'll do, okay, let's time out and let me back up a minute. I told some of you that were in here earlier, somebody decided that a bunch of us needs to go down to Tallahassee and look at a building there and the programs they've got going on in the building for something new we're going to be doing in the fall. So, and it's sometime next week. Why they chose finals week, I don't know. Decisions were made by administrators who aren't in the classroom and seem not to care about the classroom, but that's beside the point. So anyway, I don't remember what 2 days it is, but the secretary was supposed to have the paperwork done yesterday, and I was going by to sign it. I went by, and she was already gone. She said she was going to leave it on top of her desk. There was nothing there that I could discover. So I'm going to try it again tomorrow when I'm over on the Birmingham campus. If I don't get through and teaching my class until 6, and she's already gone by then, so I hope she'll have it ready for me tomorrow. And then I'll tell you on Thursday, because I'll know then for sure what my deal is on next week. But I will be gone 2 days next week. I just don't know which 2 days. That's why I want to go on, would like to go on and get the lab done for Chapter 8 this week, if I can. And then, well, no, it won't matter because it's a paper lab. There's nothing we have to actually do. So if I am going next Tuesday, I will leave that lab and stuff for y'all to work on then, and also the option of doing the test. Now, some of you were talking with me. I hope you were saying right that Tuesday is your last day.
Yes, sir.
Okay, and you'll come back for graduation if you're going to do that. Okay. So, what I will try to do, if we can wrap things up by Tuesday, if I'm here, I'll be willing to do that. Now, if I'm not here, I'll leave it, the papers there, that whoever is here administering the stuff can let you wrap up then. I just don't know when I'm gone and when I'm not. So it is, I'll try to arrange it so you can be through by Tuesday if you choose. But you don't have to be. If you want to come back Thursday and take your test, that'll be fine with me. But we are going to have the Chapter 6 test on Thursday, and then we'll probably you'll have the option of doing the Chapter 8 test and the final on Tuesday if you want to, or you can put one or both of them off until Thursday. Okay? I'll find out what days I'm going to be gone, and we'll work from there. Okay? Does someone have right now your calendar up that what days of the week, what days of the month are next week. I know, is it the 1st, 2nd, 3rd, 4th?
Monday is the 30th.
Second?
Monday's the 30th.
Monday's the 30th.
So it would be the 1st.
2nd, 3rd. Then the Tuesday would be the 1st. So if I am leaving on May 1st, I know it's May. It's not going to be in April. So if it is the 1st and 2nd, then I'll have to have somebody here administering the lab and the 2 tests if you choose to do that. And if you don't choose to do it, I'll be back on Thursday. If I'm going to be gone on Thursday, then for sure we'll try to wrap everything up on Tuesday. But if you choose not to, I'll have someone here to let you do it then. So does that sound okay? Okay, I'll give you all the options of what you're going to do. But I should know, knock on wood, by Thursday. I thought I'd know today, but she didn't have the paperwork done that I could find anywhere. Okay. Next. Student course evaluations. Have you done them?
Yes, sir.
Yes, fantastic. If you haven't, huh? Oh, yeah, you get to feel really good about yourself. Okay. That's worth more than many points, right? No, I give points for doing physical science because that's what the course is, okay? But we do appreciate and really encourage you to do these student course evaluations. That helps the next people coming, always looking ahead. Okay. And when I find out tomorrow when my trip is going to be, Thursday I'll have to let you know when the drop dead date is to have your materials in. I'm talking about your research papers and any old labs and tests that you haven't completed. Now this class has been among my best ever at getting things done on time. There's a few people, and it's not always the same person, that's missing something along the way. Not always the same person, but occasionally. Okay, never mind. But we will, I'll try to get as much back to you Thursday as possible. So please try to get everything that you have outstanding turned in to me and completed before Thursday so I can return it to you. In case I have to be gone one of the days next week, then I can get you back the materials. All right. Any questions on anything? All right. Where we left off last time was we were just about to start house. In fact, I think we had started, hadn't we? No. Go back. Okay. Where my mark is page 167, example 611. Is that about where you thought? I know y'all have been keeping up really well on that. Yeah. Okay. So, I think that's where we are. So, if you're on page 167, look at example 611. 3 resistors with resistances of 12 ohms, 8 ohms, and 24 ohms are in a series circuit with a 12-volt battery. Okay? Now, I'm going to get my... I did ask you for any questions, right? Okay. Here. What's that? Page 167. Okay, I'm going to draw a 12-volt battery. I'm just going to put 2 cells there. Actually, it would be more like 6 cells. Here's a 12-volt battery. This is chapter 6, page 167. I'm sorry? Oh, and it's a different page than that. Okay. Do they have 2 sets of page numbers?
I don't know. I guess we got a different book from you or something.
Let me see that for a minute. See. What's that? Oh, and that's why. So they changed all the pagination. Didn't know they were going to do that. Okay. All right. Interesting. Okay. 3 resistors. There's one. There's one. And there's one. That's a pretty ugly one, isn't it? Okay. Okay. 3 resistors with a resistance of 12 ohms, 8 ohms, and 24 ohms, the really weird looking one. Okay. Say again. Okay, we'll get to it. Good deal. Are in series in a 12-volt battery. Got this? Let me put that down. 12 volts. Okay. And question number A. Okay, letter A. What is the total resistance of the resistors? Did you just say it?
44.
44 ohms. Does everybody see how he did that? Since these resistances are in series, you add them up. 12 and 8 is 20, plus 24 is 44. Perfect. Any question on that? All right, the B part. The B part says how much current can move through the circuit. Okay? Now, what this is called is the effective resistance, or they sometimes have another word for it, I can't think of it, equivalent resistance, okay, of the circuit. So that would mean what the battery sees is one big 44 ohm resistor. It doesn't necessarily care whether it's 3, 7, 48, or whatever. It sees one big 44 ohm resistor. If it's a 12 volt battery seeing 44 ohms, how can you determine the current? That's what B is asking, right? How much current can you move through the circuit? Well, what formula gives that to you? I is equal to what? V over R. Excellent. Where's that from? Ohm's law. Perfect. Okay. And here's Travis. JJ. Goodness, I'm running the course, okay? Brandon. Were there any others? Is that it? 3 of you came in together, or was there 4? 3. Okay, got it. I got all 3 of them. I guess what happened, Courtney got up and went out, and I thought I saw 4 people, so that's what it was. Okay, so current is equal to voltage over resistance. What's your voltage in this circuit?
44.
Voltage. 12 volts divided by 44 ohms. If you got a calculator, tell me what that comes out being. That's 6 over 22, which is 3 over 11. 0.27. What unit? Amps. Very good. 0.27 amps. And here's Shanika. All right. Anyone else come in since I called roll? All right. Time out just a minute since several people have come in. Let me say this again. I'll try to make it quick. I'm going to have to say it every time new people come in. All right. Number 1, student course evaluations. They're out there. Please do them as soon as you can. If you want to wait till you see your grades, fine, but just please don't forget to do them. Okay? All right. Number 2. I had hoped I had arranged with the secretary to go by and sign my paperwork for, we've got a trip. Someone scheduled us for a trip next week, finals week, to go down to Tallahassee. It covers 2 days. We drive down one day, visit with them, spend the night, visit with them, and drive back the next day. Sounds like pain in, well, it's okay. All right, so anyway, during finals week, which is really a pain in the neck, okay? And what we'll be doing, I don't know which days. That's why I was going to find out when I signed the paperwork last night, but the secretary didn't leave it on her desk like she said she would. I think she forgot to do it. So I'm going to try again tomorrow because I'm on the Birmingham campus from 4 to 6 teaching a physics class, and then I go over there after 6. Of course, she's already long gone, but she was supposed to leave the stuff. So I'll know by Thursday, knock on wood, when I'll be out of town. Okay. So let's back up then from there. We should finish easily chapter 6 today. We'll start chapter 8 today. The last 2 hours today, starting at 3:45, we'll do the last lab on electromagnetism. Okay? That shouldn't take you the full 2 hours. We'll try to get through it as quickly as possible. Okay? Now, that means Tuesday. If I'm not out of town, wait. So we'll start chapter 8 today. We'll get as much of chapter 8 done Thursday as we can. Then, and that'll be 2 hours in chapter 8, 2 hours in, hopefully do the lab in chapter 8 if we get far enough along, and then 30 minutes to do the test in chapter 6. So that leaves us with Tuesday of next week, possibly having to finish chapter 8, or if we finish chapter 8 we don't have time to do the lab, doing the lab for chapter 8 on Tuesday, having the test on chapter 8 on Tuesday, and then I'm going to make it optional because several of you were saying you're leaving, most of you are through by Tuesday, right? Is that right? Well, if that's the case, I'll give you the option of doing the final on Tuesday as well. You don't have to, but if you choose to, I'll give you that option. Now, if I'm out of town, that means what I've got to do is have the lab ready for you on Tuesday, the chapter 8 test on Tuesday, and the final exam on Tuesday. You'll need to do them all if we don't have a chance to do the lab Thursday for chapter 8. So, if it turns out that I'll be in town on Tuesday, I'll be here administering all that. But if I'm going to be out of town on Thursday, it means we got to have everything finished by Tuesday. Okay? So, one way or another, we'll see how it goes. So
if you're out Tuesday,
I'll have someone here to give the test.
okay.
Yeah. I'm guessing maybe, I don't know if Dr. Thomas can. She may be giving her final. I'll have somebody, the evening coordinator, I know will do stuff like that. So we'll do. So we'll talk about it more on Thursday. I should know right now, but I don't because she didn't have the paperwork ready. Okay. So we found the by Ohm's law, the current for this circuit is 0.27 amps. The C question says, what is the current through each resistor? What's the current through the 12 ohm, the 8 ohm, and the 24 ohm resistor? Any ideas? Again, this is a series circuit. All the battery C's, you might say, is one big 44 ohm resistor there. So the whole current goes through every one. Where else can it go? There's only one pathway. So through each resistor is 0.27 amps. It can't be more through one and less than another because it's all going through the same circuit. So the answer to C, every one of them, 0.27 amps going through it. In a series circuit, the current is constant, the voltage drop differs, and of course the resistance differs. Okay? And then we'll do the next one on figure 611. Example 612. Okay. Now, let me back up just a minute before we go to 612. I think we talked about the blackout reveals pollution on page 167, top of the page. I believe we mentioned that and moved on. There is a good little blurb here on page 168. It takes almost the entire page. It's a closer look. And this is taking a closer look at solar cells. Now, this might give you a good idea for a paper. And by the way, people, I'll let you know, if you can get your papers in today, tomorrow, or Thursday, that would be great. I'll be on the Birmingham campus Friday. I'll take them over there if that's convenient for you. I'm pretty sure I'll be on campus Monday of next week, too. Get them to me then if you can. But I don't know what day we're leaving town, and I don't know which day we're coming back. So you have to turn in your papers by
Monday.
Tuesday of next week. That's the last day of class. Okay? But I may not be here. So whoever's up here administering your test, turn in your research papers to her or to him, whoever it happens to be. I would like you to get all your labs and tests finished by Thursday if possible. I would love to turn back as many of those as I can to you because I may be out on Tuesday and I won't see you to give you the papers. I'll leave them with whoever's going to be here, but I won't be here to give them to you. Okay? So please try to get as much in as possible today, tomorrow, Thursday, or Friday. Or Monday. I'll be here Monday, I think. Pretty sure. Okay. So, this might be a good paper topic. Solar cells. How do they work? That kind of stuff. Guess what, though? This can't be your source for your paper. The source has to come from outside the book. So be sure that if you do get interested in reading this, be sure that you get your source from elsewhere. Okay? And this may even have some sources in it that you can use those sources. Okay? But it has to be from outside the book. Okay, so read that. It has a pretty good description of what's going on with the solar cell. Okay? In fact, remember when we talked about semiconductors? That's basically the heart of a solar cell. It conducts electricity one way, but not the other. Okay? Under certain conditions, not the other. So, I highly encourage you to read that. All right, let's do example 612 now. Assume that the three resistances in example 611, 12, 8, and 24 ohms, are now connected in parallel. And we'll answer the same questions. So I'm going to erase these and have to redo them. Okay? So here will be my battery again. 12-volt battery. Okay. V stands for voltage or potential difference, but it's also the unit for voltage. So V is the same in both. Okay, and now we're going to do a parallel circuit. That's a pretty ugly parallel circuit. Okay, let me draw the next one better. Okay. Okay, that's your parallel circuit. Pretty ugly, huh? This was a 12 ohm battery. This was an 8 ohm battery. And this was a 24 ohm battery. All right. That's what it says. Assume the three resistances in example 611 are now connected in parallel. What is the combined resistance? How do you come up with the combined resistance of a parallel circuit? In a series circuit, you add the resistors. In a parallel circuit, how do you get them? The blank stairs. How do you get them? Okay, I'm going to scroll back a few. Actually scroll ahead. Okay, there is a picture of a parallel circuit, and there is how you get the effective resistance, or the equivalent resistance. 1 over the effective, this book calls it total resistance. Kind of don't like that because it carries the connotation of adding them up. You don't. But 1 over the effective resistance is equal to 1 over the first, plus 1 over the second, plus 1 over the third. As many as you got, we got 3. So that's the formula we're going to use. Okay? So let's go back to 1 over, and what did they call it? Combined resistance. Let's call it RE, effective or equivalent, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, thankfully, they gave us resistances that are multiples of each other. Okay? So it'll be 1 over 12 plus 1 over 8 plus 1 over 24. How do you add fractional forms? Anyone remember? No, math was a long time ago.
Get the same denominator.
Okay, and what would be the common denominator of those three? 24. Okay, so we're going to put each one over 24. I'll do the last one. 1 over 24 is the same as 1 over 24. I got that. Okay. Now, how many 24ths is 112?
2.
2 24ths. Great. You multiply the denominator by 2, multiply the numerator by 2. How many 24ths is 1/8?
3.
3. Very good. Y'all are good at this. And what do those add to?
6.
Say again?
6.
6 24ths. Can you reduce that? 1 over 4. And this is your effective resistance. 1 over the effective resistance is 1 over 4. That means the effective resistance is 4 ohms. Bizarre but true. The more resistances you put in a parallel circuit, the more the resistance goes down, not up. Okay? Notice the effective resistance is less than any one of those, and it always will be. Okay? And the more you add, the more it drops. That's amazing but true. Okay? So your effective resistance, this is question A. What is your effective resistance? Or the book calls it combined resistance. The B question here says, what is the current in the overall circuit? Okay? Now again, this is not probably the best way to think of it, but think of this battery as here is making decisions. Of course it doesn't, okay? But let's say it's looking at this stuff out here. It doesn't care you have 3 resistors in parallel. All it sees is an effective resistance of 4 ohms. So therefore, what is the juice that it's going to have to get? Yes, because of Ohm's law. I is equal to V over R. That would be 12 over 4. So this would be, the B part would be 3 what? Amps. Everybody see that? Just like we did before though, it was 44 ohms, so it was a lot less current. This is 4 ohms effective resistance, so that's going to be 3 amps. A lot more current, okay? And the C part, what is the current through each resistor? Okay, we're going to have 3 different answers here. Why? What is the voltage across this resistor? 12 volts. How many, what's the resistance here? So what's the current through here? 1. So 1 amp goes this way. Okay. What's the voltage across this resistor? 12. Same 12. And what resistance? 8. So what's the current? 1.5. 12 divided by 8 is 3 over 2, so that's 1.5. Your current here, is 1.5 amp. Okay? And what is the voltage across this resistor? 12. And what's the resistance? 24. And what's the current?
2.
Say again?
2.
Okay, how did you get that? What's the formula? I is equal to? Ohm's law?
V over R.
Oh, V over R.
Yeah.
Now, what does that give you?
Half.
0.5, yes, 1/2. So this current will be 0.5 amps. And that sort of makes sense. It's a bigger resistor, so less current is going to go through it. And by the way, what do these add to? 1 and 1.5 is plus 1/2. There it is. Your 3 amps. So in a parallel circuit, the currents add, the voltage stays constant. Remember, in a series circuit, the current was constant, and the voltage dropped differently across each resistor. But in this one, the voltage is constant, the current drops across it. The current through each resistor is different. And they add to the total current. So that was right here, 1 amp, 1.5 amp, and 0.5 amps. All right, does that make sense? And that's what the book got to. Good for them. All right. Now, with that in mind, let's now go to your household circuits. Okay? Now, hurt my knee a little bit over the weekend, so it's fine when I'm up and moving, but when I sit for too long, it gets stiff. And getting up makes it really hurt. Okay. So in household circuits, we usually have a combination of series and parallel circuitry. Now, most of your things in a household circuit are not in series with each other. Otherwise, when you turn off the mixer, the TV goes off. Okay, we don't want that happening. Okay, so most things are in parallel in the thing. But what has to be in series? For instance, these lights up here. Are they in parallel or series with one another?
Series.
Really? That means if they got a bulb, they all go off.
No, but you flip the breaker and they will.
Okay, now, they're in series with the switch, but they're parallel with each other. And that was my question, what are they in relation to each other? They have to be in series with the switch, otherwise they wouldn't necessarily come on or wouldn't go off, you know. So they have to be in series with the switch, okay? This light is, but it's in parallel, those bulbs are in parallel with each other. Otherwise, you pull one out and they all go out. Y'all don't remember the old Christmas tree lights, do you? Oh, yeah. If one went out, the whole line went out, and then you had to find out what was wrong. That was a real pain. Okay. Now, another thing that's in series with it, and you mentioned this, the breaker. Okay? And here's why the breaker needs to be. Because if you add more appliances in, how are these connected? Parallel. Every time you add something else, the resistance drops. Remember, we saw that. Okay? So therefore, the resistance going down, the current has to pick up. Okay? Because you got the same voltage across here, 120 probably, and every time you add something else to it, that 120 is having to provide more and more current. And Josh is here. Okay. And after a while, if you just keep doing that, you got an awful lot of current through here. And too much current is going to do what? Yeah, it'll overheat the wires if you didn't have a breaker there, and therefore you need the breaker. And once it exceeds what that breaker is set for, it trips to make it stop. The old days they used fuses, and then they blew. Okay, and then you have to replace the fuse, and you better get the circuit fixed first, or you're going to blow another fuse. Okay, so the circuit breakers are more durable and longer lasting, and you can deal with them. Okay. And here we show a toaster, a can opener, and a radio. Which of those is probably going to draw the most current?
Toaster.
The toaster. Anything that produces or deals with heat, that's going to be the greatest. Between the can opener and the radio, I don't know, probably can opener a little more than the radio. Okay? But you keep adding things, you drop and drop and drop the resistance. Okay? So the combination of series and parallel circuit, the light fixtures in the room are in parallel with one another, but they have to be in series with the switch, otherwise the switch doesn't work well. Generally, all your plugs are in parallel with one another, even the two plugs on the same outlet. And here's Coco. Okay? They are in parallel with one another, and the more things you have plugged in, the more your resistance drops and your current increases. Okay? Now, what makes all this true? When the appliances are in parallel, which they usually are, the same voltage is available to each one. If the same voltage is available to each one, it's got to provide enough current for that, okay? Because so there your voltage source is having, the more you put on there, the more it has to supply current. The circuit breakers and fuses prevent the overload from happening, which you can have if you put too many things on. The first old house that we rented when we moved to Birmingham was a neat looking old house, and they said, and we've upgraded the kitchen. Okay? The electrically, we totally upgraded the kitchen. Okay? And sure enough, there were new plugs all over the kitchen, you know. So you could have your microwave, your coffee maker, your refrigerator, your, I can't remember if we had electric range or gas, I don't recall now. But all these things, you had plugs all over the place. Of course, if you ran more than 2 or 3 devices at the same time, it blew the fuse. It was an old house. It had fuses. We kept Big B, which was the old drugstore in town then, in business buying fuses. Because if my wife was making coffee one morning and it happened to be the refrigerator kicked in, the compressor on the refrigerator kicked in, there would go a fuse. And that was the only thing she was doing, was trying to get her coffee maker to work. And she had no control over the refrigerator. If that compressor turned on, the whole thing went off. All they had done is, on one single circuit that kitchen had, they had just put more and more and more plugs around the thing, so it did not work very well. Thank goodness they had fuses on them. Otherwise, the house could have burned down, you know, because it was really poorly done. Now, upstairs in the bedroom and in the dining room, living room, and every place else, one outlet per room. So we had extension cords running all over the place along the walls, which was, again, putting parallel circuits in, but we were very careful. We just needed things for our clocks, the lamps, and things like this. We couldn't plug the 2 things in at a time. So we had a bunch of extension cords, which can also be somewhat hazardous too, because remember, the length of the cord adds to resistance as well. Okay. That's household circuits. Now, household circuit safety. Okay. I think this may be the last the last slide. There's a plug there. Okay. The potential difference from 2 wires per device. Now, in the old days, you didn't have 2 different sizes of things here. And you certainly didn't have a ground on it. In the old days, you just plugged it in and the current went wherever it wanted to. Why do they have a big and a little plug there? Anyone know? Okay. Say again? Yes, you always have the hot line on one side and the ground on the other. The potential difference from 2 wires per device, you have the energized load carrier. Now, in my mind, I thought that was going to be the big one. It's not. It's the little one, okay? And the other is the ground, or the neutral wire, okay? So that way, all your devices are set to, this will be the hot side, this will be the ground side. Now, this is not a 3-prong plug. I sure don't see a 3-prong down there, but this is a 3-prong outlet that provides yet a backup grounding wire. Okay, not just the ground for the whole circuit, but a separate ground that if you did overload, it's going to take it to ground. Okay, that is a safety feature. Now, other devices, polarized plugs. This is a polarized plug. A lot of your things, like my computer here, I'll unplug it for right now. That's not a polarized plug. These 2 are identical. It doesn't matter to the device which is a hot and which is a cold, ground, because it's converting them to DC anyway, okay? So there's no need for a 3-prong plug there. However, I've noticed most HP products, even though they have a converter on it, they still have a 3-prong plug. Or at least a polarized plug. This one does not. Now, does anyone know what a ground fault interrupter is?
Yes.
Okay, what does it do?
It's pretty much a breaker built into the outlet itself.
Exactly. It's yet another safety level. The polarized plug gives you a little bit of safety. The 3-prong gives yet another, and then the ground fault interrupt is yet another level. I don't know if you remember, you probably don't. Back when I was, as Garland Corley used to say, a boy child, okay, and some of the old TV shows, especially the mysteries, one of the favorite ways to do someone in was, if they were in the tub, drop in the radio, okay? Electrocute them on the spot, or the hair dryer, or whatever, okay? And I've actually seen still people suggesting those kind of things. But the thing is, most of your kitchen, bathroom, and outside outlets should now all be GFI, ground fault interrupt. So just like what you said, it's sort of like having a special fuse or circuit breaker within the plug itself. If it senses a big burst of current, then it's like a circuit breaker and breaks. So I think theoretically, if you were in the tub listening to the radio and knocked the radio in, it shouldn't fry you now, okay? Because the ground fault interrupt should interrupt the circuit before that were to happen, okay? So that is the last slide in the set. I know you can't imagine what I'm going to say next. Nothing replaces reading the chapter, okay? And if you haven't already, please, it's a good idea to read it ahead of time. Therefore, anything I say builds on what's already been placed somewhere in the synapses of your brain, and it makes more sense, okay? But at least now that we've talked about it some, if you go back and read it now, maybe when you read it, those synapses are in place, okay? It's better to read ahead of time. But once you've read it, then there is a summary, and this is one of the longer summaries. It's almost a half page on page 171, and more than half a column on 172. So it's a pretty good-sized summary. Summary of equations, 11, which is more than most chapters, pretty much by far. Key terms, that looks about normal. It takes up the bottom part of the column on page 172 and the top 5 on 173. But then applying the concepts, this is probably the best thing to study for the test. 50 questions with probably a few more than normal. These are all multiple choice. Now your test will not necessarily be multiple choice. The majority will be multiple choice. There will be probably 1 or 2, like you usually see, short answers, and another 1, 2, 3, maybe up to 4 might be actual calculations, okay? I can't remember for sure. I can remember 2. I just don't remember if there's 2 more scattered out throughout the test. So, but if you got the multiple choice down, now these aren't the same questions you'll see on the test, but they're covering the same material. So if you got these down, you probably have a pretty good idea on what, and the answers are provided here. In the earlier editions, students would usually find something. They said, I don't see how they got this answer, and we look at it. About half the time we find out the answer was wrong, but the other half the time the students' thinking was just wrong. So now questions for thought, there's 12 of them. That's actually fewer than most chapters have. For further analysis, there's 7, which may be maybe 1 or 2 more than normal. Okay, there's earth power here. Good little thing to think about. If that leads you to a paper topic, that would be good. But then there's the parallel exercises. So only 17 questions in each, both Group A and Group B. However, remember 11 equations. There's probably each one is represented at least one of these questions. So there's not too many duplicates here. So these would not be a bad thing to do for your test. If you have a big book, the answers are in the back of this. I asked them to put it into the smaller edition, but so far I haven't found it there. If those only Group A answers would be in the back if they're there. I sort of expect they're not. Okay, I wish we had time to do Chapter 7. great chapter on light. We don't, okay? We're supposed to have a little bit of chemistry, so that's what we're going to be doing in next. We're going straight to chapter 8. For those with the smaller book, you don't even have chapter 7. We're going straight to 8. Any questions on chapter 6? And let me remind you, in case any of you came in, I know Coco came in, let's just do a real quick recap on what's coming up toward, because we're right at the end of the term. Number 1, have you done the student course evaluations? Okay, several of you have. Do any of you not know how to access those? You all received an email, whether you realize it or not, that had a link to the student course evaluations. What confused a lot of people, and it confused me until finally I figured it out after quizzing some students. I think it was in here. This class helped me figure it out. The student course evaluation link was in the email that was about Student Government Association elections. It said nothing about student course evaluations. And a lot of people just ignored the email because they didn't care about student government or whatever, okay? And so they never saw the link to student course evaluation. So if you go back to your email, find that email that dealt with student government elections, and that one is a link to how to do your student course evaluations. Please do those. Number 2, I was supposed to find out yesterday, but the secretary didn't have it ready, the paperwork for a trip. I'm going for 2 days to Tallahassee next week. I just don't know which 2 days. That's why I was looking forward to seeing the travel request that she had volunteered to do for me. And so I just don't know which 2 days it is. But we'll start chapter 8 right now and do that until 3:45. 3:45 we're going to do our last lab for chapter 6. We'll get that done, and then Thursday, hopefully we'll come close to finishing chapter 8, okay? But by Thursday, I'll know when I'm out of town. I just don't know right now. So, if I'm going to be out next Tuesday, we're going to get as much of chapter 8 done as we can on Thursday, and I'll give you the lab for chapter 8 on Thursday. If we don't finish the chapter and I'm going to be in town on Tuesday, then we'll wait and do the lab on Tuesday. Okay? But definitely on Thursday we'll have the test on chapter 6. So we'll do 2 hours of class on chapter 8, 2 hours of lab. Back up. We'll do at least 2 hours of chapter 8. If we can finish the chapter, we'll go on and finish it, especially if I'm going to be out of town the next Tuesday. And then you might do the lab on Tuesday. If I'm going to be in town on Tuesday, then we'll end at 2 hours of class and probably do, we'll go as far as we need to, and then have the test on chapter 6, the last 30 minutes on Thursday, this Thursday. And then the next Tuesday, if I'm here, we'll do the lab on chapter 8, the test on chapter 8, and I'll give you the option of doing the final in chapter 8. If I'm not going to be here, I'll have someone up here, and they will have all 3 of those documents, and you can do those as well. All right. Been through that enough. I'm almost confusing myself. So let's move on to chapter 8. All right. There it is. I wish we had longer in chemistry. It's a great subject. In this first chapter, frankly, I found to be a little on the dry side. They cover so much background stuff, you don't really get to do that much that's fun, though it's all fun. And for some reason, chapter 8's not opening. I don't know what's going on here. Let me try this. Sometimes you have to rattle its cage. Okay, it's running, but it's not indicating. So let me try this. Nope. Ah, there it is. I guess rattling its cage did work. Okay. All right, here we are, Chapter 8. Atoms and periodic properties. I can't remember what the significance of that picture is, but it must have some significance. So here's the core concept. This is on page 205 in the big book, and I guess the pagination is different in the small books. But the core concept here, different fields of study contributed to the development of the model of the atom. We've already talked in the small amount about the concept in physics. Certainly that contributed a lot. Most of the rest of it came from chemistry, but it came from all over the place, okay? But mostly physics and chemistry. So, we'll talk first, and to me, by the way, that was a pretty weak core concept. There's a lot of things I think could have been said in addition to that. But I think we've already mentioned this before. When the atomic structure was how it was discovered, the very, very, very ancient Greeks, this is 400 to 300 BC, before Christ, way back, Democritus, who came along maybe 100 years before Aristotle even, he thought there were indivisible particles called atoms. I've given that illustration before. What if you had a bar of iron or gold or whatever you wanted, you broke it into smaller and smaller pieces, and you kept breaking and breaking and breaking until you got the tiniest piece that you could have, that you couldn't divide any further, and that was an atom. The word atom came from the Greek word indivisible. Okay? That was the concept. And that was just a thought experiment of his. He had no equipment to do that, but he said, there's got to be some smallest piece before that quits being iron. The smallest piece would still be called iron. Well, then came Plato and Aristotle, and their idea was matter is continuously and infinitely divisible. In other words, it was just a continuum, and you could always keep breaking and breaking and breaking and breaking and breaking and never get to that smallest piece. So people, Democritus had been long dead, so they quit listening to him, listened to Plato and Aristotle because they were the honchos. Well, they were wrong. Okay. Now, they were about 300 to 200, maybe even 100 BC, somewhere around in there. Not long before Christ, okay? Then John Dalton. This is 1,800 years later. Clear 2 millennia after Plato and Aristotle. Okay, close to it anyway. He came up and reintroduced this atomic theory to explain chemical reactions. Basically what he and many others had noted, and this is why they say many people contributed to this. Based on Aristotle, Aristotle said there were only 4 elements. Remember what they were? 3 of them made a singing group. Y'all don't remember that. It was way before your time. Earth, wind, and fire. Ever heard of them? No, probably not. Okay, that was a singing group. The 4th one was water. Earth, water, wind, and fire. Aristotle said everything's made up of those. Well, he had no proof. It was just one of his ideas. But everybody accepted it because Aristotle said it. Right, we'll buy that. Well, in the 1700s, even probably back into the 1600s, they said, hey, Earth is cheap. You can go get it for free. Air, wind is free. It's all over the place. Fire, you have to pay to get it, but you can come up with fire pretty easily, cheaply. And water is all over the place, okay? So look, if everything's made up of this, then we should be able to combine earth materials, air, water, with enough heat and get anything we want. Like gold and platinum and silver and valuable metals, hey, we'll do this, okay? We can make a killing here, as my mother-in-law says sometimes, okay? So they started doing it, and these were called the alchemists. And they started experimenting with combining these various materials together, trying to come up with valuable stuff, taking cheap stuff and making valuable stuff from it. Well, they found out after a while, when they first got started, they had to keep really good records, because then they'd be repeating the same thing over and over again. So they were meticulous in their record keeping, okay? And they were, well, let's try a little bit of this, let's try a little bit different of this, a little more heat here, mixing here, doing whatever here, and they tried all these different things, and over time, John Dalton, he was probably doing it too, but others were doing it, and he was reading their notes and write-ups on things, and he found out, there's certain reactions that always combine with the same ratios. And in chemistry, this is called the law of definite proportions. If you take 5 grams of hydrogen and 10 grams of oxygen, okay, combine them together, you'll have some hydrogen left over. If you take 20 grams of oxygen and 2 grams of hydrogen, you'll have a little oxygen left over, because they always combine at the same proportion. Doesn't matter if you have excess of one, whatever the limiting factor is going to limit the whole thing. So he said there's got to be indivisible units in here, atoms, that combine at these certain ratios. Now his theory was these various things had hooks on them. This is just a model. He didn't really think there were hooks, but they acted like there were. Say oxygen always seemed to have 2 hooks, and hydrogen 1 each. So you do a hydrogen here, a hydrogen here. What do you have? Water, H2O. And if you had carbon, carbon always had 4 hooks. And if you had 4 hooks here, 2 hooks here, 2 hooks there, 2 oxygens here, 2 oxygens there, what do you have? CO2, carbon dioxide. So everything seemed to work that way. He noticed and repeated, so he figured they had to have certain indivisible units, that when you get down to those, you can't get any smaller. Okay? Now this is a nice looking, but maybe hard to see, illustration here. It's not at all realistic. It's a little bit realistic. This is the model of an atom. In the middle of the atom, you have what's called the nucleus. Now this nucleus is way, way, way too big for this atom. Now, admittedly, the nucleus has almost all the mass of the atom. Almost all the mass is concentrated in the nucleus. But it's a tiny little nucleus. It's just extraordinarily dense. Unbelievably dense. Okay? And it's made up of protons and neutrons. Now, I don't know which is which here. One of these represents protons, one neutrons. Doesn't matter, it's just a representation. And they're massive. They're really, really massive entities, but they are fixed together in the nucleus. Okay? Now, flying around them are electrons. Now, these are not individually electrons. These are places those electrons may be. And you'll see there's one cloud here, and then another cloud out here. Now, I bet you from where you're sitting, you probably can't tell that distinction, but this is 2 levels of electrons. I'll tell you right now, there's only 2 electrons in the inner level, but they may be any of these locations, so that's what all the little specks mean. And there's up to 6 electrons in the outer level, and they can be anywhere in there as well. Okay? That means, and by the way, for this to be a neutral atom, which of these particles are charged? Any of them? I mentioned 3. Protons, neutrons, electrons. Protons are positively charged, but neutrons are negative. Neutrons are neutral, no charge. That makes electrons negatively charged. And even though the proton is an enormously massive quantity, it has the same charge as that almost massless electron. Okay? They each have a single charge. It's just protons are positive, electrons are negative. The neutrons, with no charge at all, are actually slightly more massive than the protons, even though the protons have charge, neutrons do not. Not much difference. Now, for that to be realistic, the nucleus would be like one of those little dots down there, and the electron cloud would be huge, because that's the difference in size, but the difference in mass, all the mass is in the nucleus to speak of. An electron is about 1/10,000th of the mass of either a proton or a neutron. I mean, that's very, very small. Okay, so here's Dalton's atomic theory. And by the way, John Dalton would be a great paper topic, wouldn't he? Or how did he develop the atomic theory? Or what was, there's lots of different things to do. Now, based on this, all matter is made up of indivisible atoms. Now, there's different types of matter. One bit of matter would be an element. Can anyone name a few elements for me? Now, a neutron is a particle within the nucleus. What would be an element? Name an element. I've named several already. Oxygen, hydrogen, carbon, nitrogen. All those are elements. What does it mean to be an element? Every atom in that element is identically the same. If you had iron, that piece of iron, if it's pure iron, every atom in there is an iron atom. Nickel, cobalt, copper, aluminum, all those are elements made up of identical atoms. Okay? Different elements have atoms with different masses. Okay? In other words, all iron atoms have approximately the same mass. They may differ a little bit, but not very much. But different things, iron and nickel, they're right next to each other in the periodic table, they have significantly different masses. Not much, but a lot more than the different things. So different elements have atoms with different masses. Okay? Now, those are elements. The second class of material would be compounds. Oh, and by the way, let's back up. Remember in chapter 4, we sort of started talking about what's happening on the macroscopic scale and what's happening on the microscopic scale, submicroscopic. Same thing's going on here. Elements are macroscopic concepts. Atoms are the microscopic concepts that make up the elements. Same thing here. Chemical compounds, that's a macroscopic concept here, made up of atoms in specific energy ratios. That's what I was talking about, the law of definite proportions. Can anyone name a compound for me? We've already named at least two today. H2O, that's a compound. It's made up of two different elements, hydrogen and oxygen. There's two hydrogens connected to each oxygen. Specific integral ratios. That's what led Dalton to say these have to be indivisible little units here, because they always go on these ratios. Okay? So chemical compounds are made of atoms of specific energy ratios, generally atoms of different materials. Carbon dioxide, ammonium, calcium carbonate. I mean, there's just tons. Okay, back on elements. In the neighborhood of 100, 109, 118, somewhere in there, there are different elements. And that's all, folks. Some fixed, fairly large, but not too large, finite number. It's all the elements we have. Compounds, they can be put together in many, 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 many different forms. So chemical compounds are made of atoms of specific energy ratios. Atoms are neither created nor destroyed in chemical reactions. Mass is not created nor destroyed. Charge is not created nor destroyed. Neither are atoms. Atoms are indivisible. Well, not quite, but close. In chemical reactions, they're never created nor destroyed. You just rearrange them. Have pure oxygen, O2, which actually is one molecule of oxygen, which is two oxygens tied together, and split that up and put two hydrogens on it, and you got water, or two, any of it hurts. All right, here's Justin Struthers. Okay. Anyone else come in since the call roll? I think the last one was Coco. I did get it, didn't I? Yeah. Okay. And by the way, sorry for you people who were earlier. You've heard this before, but I want to make sure everybody hears it. Okay? Please do the student course evaluations if you haven't already, right? Justin, have you done the student course evaluations? Justin? Okay. Have you done the other one too? Both of you, okay. Have you done the student course? Oh, all right. Fantastic. Okay. Secondly, how we're going to end the term. Okay. We have class today. We have class Thursday. And we think we have class Tuesday. We're supposed to have class Tuesday. But the bad news is they've scheduled me and a group of us to go out of town during finals week. We leave one day, come back the next day, spend one night. So I'm going to be out 2 days next week. I just don't know what 2 days. They haven't done the travel request yet. She was supposed to have had it done by last night because I went by to sign it, but she was already gone and she didn't leave it on the desk where she said she was. So I don't know what 2 days it is. I can probably check on email somewhere, but I haven't done that lately to see. So whether I'm here or not on Tuesday of next week, that's when your probably your last lab, your last test, and the final exam will be. If I'm here, I will administer them. If I'm not here, I'll have someone else to administer them. Okay? So be prepared for that. Try to have all your labs, all your tests, everything else completed by Thursday. And I should know on Thursday what day I'm going to be out. Actually, what days I'll be out. Okay? So I will try to let you know that on Thursday because I'm going to go by again tomorrow to sign my travel request. If she has it ready, I'll try to give her a call either today or tomorrow to remind her to have it out there for me. Okay. And if I'm going to be gone Tuesday, then I'll be here Thursday. If I'm going to be gone Thursday, then I'll be here Tuesday. So I just don't know which days it is. All right. Any questions on Dalton's atomic theory? Okay. Now, we started basically modern stuff with John Dalton, early 1800s. That's when chemistry basically started moving from alchemy, which was sort of magical type stuff, to an organized science, and John Dalton did a lot of that. Okay? Now, the late 1800s, sometime later that century, this guy named J.J. Thomson, I'm pretty sure he was from Britain as well, he came up and discovered, even though people had been using it for a while, the electron. Okay? He was performing some cathode ray tube experiments. Cathode ray experiments. Basically what that is sending high energy beam through usually copper, but it could be other things, molybdenum, some metal, and things would be coming out of it. He discovered that these things are negatively charged particles with almost no mass at all. I don't know if he named them electrons, but he is credited with discovering the electrons. So they have been here forever. Back when, remember, they would rub fur on amber and shock people, that was exchanging electrons. Of course, no one knew what electrons were, but that's what they were doing. So he actually discovered what those things were and did some quantifying. Here was the problem. Those things are incredibly tiny with almost no mass at all. But they have a charge. So all he could do was measure the charge to mass ratio. He couldn't determine either the exact amount of charge or the exact mass, but he could come up with the ratio of the charge to mass. And he identified the electron as a fundamental particle. Okay, now here's a little problem with Dalton's theory now, and even Democritus' theory. Remember they said these atoms were indivisible? Well, they discovered you can break off at least a little bit of it, the electron, and send it somewhere else. Rubbing fur on amber, for instance, did that. Okay, so here's a fundamental particle in every atom that can be separated from the atom. Not usually, but some of them can be. So that was J.J. Thomson. Now here's a picture of the cathode ray tube. Now for this to work at all, you had to have just about all the air extracted. So they show a vacuum pump. And this is why by the 1800s they were able to build pumps that would pump out most of the gas particles and leaving very strong reinforced tube here. And what they did, they put a very high voltage. This came after Volta had done their experiments and they knew how to use batteries. So very high voltage, plus in here, minus in here, and very high voltage across this. And they found out these cathode rays would leave the cathode, that's the minus side, moving toward the anode, which is the positive side. Okay? Now, what those cathode rays were, they were your electrons. Because if you think about it, if you're building up negative charges here, what have you got? Excess electrons. Positive charges, you don't have excess protons, you have a deficit of electrons. Protons don't move, they stay in that nucleus. It's the electrons that move, and that's what's happening here. And you have the cathode rays going. And like I said, I think usually the cathode, I'm not certain, but it seems like it's usually copper or something like that. I may be confusing it with an X-ray diffractometer. I know that's copper most of the time. Okay. Let me get Lauren here. Okay. Let's see. Did I mark Alexis when you came in? Yes, I did. Okay. Sorry for the rest of you. You'll hear it again. Have you done the student course evaluations? No. Do you know how to do those? Okay, you know the link to get to them? Okay, good. That was buried in an email that dealt with SGA elections. It didn't say anything about student course evaluations in the title, but that's where the link is in that email. Okay? Now, let me again go over real quickly how we're going to wrap up. We finished chapter 6 earlier today, so that means on Thursday, the last 30 minutes, we'll have the test on chapter 6. So that's a done deal. The last 2 hours today, we're going to have the last lab in chapter 6, electromagnetism. So the rest of the day up until 3:45, we're doing chapter 8, and then beginning on Thursday, for at least 2 hours, we'll do chapter 8. Now, if we finish all of chapter 8 between today and those 2 hours on Thursday, then we'll have the lab on chapter 8 on Thursday. Don't think we'll get that far in chapter 8, so I doubt if we'll get that far. So my guess is we'll get as far as we can in chapter 8, but the last 30 minutes will be the test on chapter 6. Now, what I might do for y'all, if you want me to, is have the lab. The lab for chapter 8 is a paper lab. You'll use the book, the text, and just fill out paperwork, okay? Unlike the hands-on stuff we've been doing in the other chapters, most of the other ones. So we'll see. I may just hand it to you and let you have it, and we'll do it in class on Tuesday if I'm here, okay? If I'm not here, y'all will have to, in class, work together or something. That's why I may go and give it to you. But I should know by Thursday whether I'll be here or not. Okay, so that then puts what's happening on Tuesday. Well, if we finish chapter 8 on Thursday, we'll have the test on Chapter 8 on Tuesday. If we finish it but don't have time for the lab, we have the lab for Chapter 8 on Tuesday. But I'm also giving y'all the option, only if you choose to, you can elect to do the final exam on Tuesday too, if you wish. Because I'm going to be out 2 days next week, and I don't know which 2 days. They told a bunch of us we have to go to Tallahassee. We drive down one day, spend the night, and drive back the next day. So we're going to be there late one day and early the next day. And I just don't know which 2 days. If it's Tuesday, I'm going to be gone. Then I'll have somebody else up here giving you the lab and the Chapter 8 test and the final exam. If it's Thursday is one of the 2 days, the second day I'll be gone, then I'll be here on Tuesday. I'll give you all that then, and we won't have class at all on Thursday. Okay? So that's how we're going to wrap up the term. But I want to, for everybody, I may not have said this for everyone, I want you to get as much into me as possible by Thursday. Old labs, tests, whatever. I want those all done so I can give them all back to you as soon as I can. They'll definitely go back to you by Tuesday of the following week, but I'd love to get them back sooner. Okay. So this was J.J. Thompson's cathode ray tube. Those cathode rays were actually electrons moving from the cathode to the anode, from the negative to the positive, because electrons are negatively charged. Okay. Now, that's what he was doing. How did he discover that charge to mass ratio? How did he identify that these were indeed electrons? Well, he did something more. He was working with a cathode ray tube. Here's that negative plate here, and you just don't see the positive plate over here, but there is one, something pulling off, attracting those electrons. So he didn't know they were electrons. Okay? And for the life of me, I can't figure out what in the world that stands for. It has a big plus in it. Oh, I guess I know it. This is the positive part of the cathode ray, but it's hollow. Okay? And the rays go here, and then it has two charged plates here. One charged positive, one charged negative. And these electrons, which they turn out being the cathode rays, are attracted to the positive plate and repelled from the negative plate. Now, he also has this in a magnetic field. Strong permanent magnet here. Okay? And that creates something that we haven't talked about or won't deal with yet. But anytime you have a moving charge, you have an induced magnetic field. So you can also detect the effect of the magnetic field. Okay? And then out here on this end, he has a detecting screen. And what he noticed that the charges were deflected toward the positive, away from negative. So that gave him that piece of information. He also had the deflection because of the magnetic field. Okay? That gave some information. And by studying the deposits here, he came up with the deflection depends on the charge to mass ratio, because the bigger the object, the less it was deflected, the smaller the object, the greater the reflection. So by the studying that, which had everything to do with the mass of it and the charge, he could get charge to mass ratio. So this is a real thumbnail sketch of a pretty involved experiment here. The positive and negative charges are deflected in opposite directions, and the detecting screen picks that up, and the amount of deflection on the negative particles depended on the charge to mass ratio. Okay? So, that was the how he came up with it. But he couldn't figure out either the total charge or the total mass. They were both incredibly small entities, but he could come up with the charge to mass ratio. All right. Then came a guy shortly after. Remember, J.J. Thompson was late 1800s. In 1906, or around about then, a guy named Robert Millikan came up with another experiment. And this was a pretty nifty one. What he did, especially you gals I know probably have spray perfume things, right? That you squeeze a button and little droplets of perfume, go wherever you're spraying them, okay? But he did this with oil droplets, okay? He would spray just a few, they call it an atomizer, even though it wasn't as small as an atom, but very, very fine droplets of oil. Spray it, and it fell through an electric field, okay? Now, the charge on the droplets equals multiples of the electron charge, okay? Because in an electric field, you have picking up electrons, because that's what's moving, okay? And the droplets would pick up electrons. If it picked up a single one, that would be a single electron charge. If it picked up two or three, they would all be multiples of that single electron charge. So, since he was able to determine at least the multiples of the charge, he could get, just like we did, least common denominator, get down to the smallest charge he thought it was with that charge, and Thomson's result of a charge to mass ratio, he could come up with the electron mass. Pretty clever. Within about 10 years of when J.J. Thomson had determined that ratio, Millikan came up with this experiment that actually, by calculation, gave him the mass. Okay. Now, I was really lucky, I guess. I didn't maybe consider it so at the time. I know you're in here. Gary, there you are. All right. Time out again, so y'all are going to get tired of hearing this, but I want to make sure everybody gets a chance to hear it. Okay. Number one, have you done the student course evaluation yet? No. You know how to access it? You do. It was in an email. Okay, you know that email. Okay, good. All right, please do those sometime before the end of the term. Okay. Number two, this is not definitive, but parts of it are. We finished chapter 6 earlier today. Okay? We're in chapter 8 right now. Okay? We're going to continue in 8 until 3:45. At 3:45, we'll have the last lab in chapter 6, which is electromagnetism. Okay? And you'll probably finish that before the 2 hours are up, but that's the last 2 hours of today. Thursday, this coming Thursday after tomorrow, we'll continue with chapter 8. Okay? The last 30 minutes of that class, you'll have the test on chapter 6. Okay? Now, if we finish chapter 8 on Thursday, which we may or may not, I think we will, we may not have time for the lab for chapter 8. Now, it's not a hands-on lab, it's a paper lab. You read the chapter, you fill in the paperwork. Okay? So, okay. Back up. Somebody decided that a group of us has to go out of town next week. And we're going to be gone 2 days, spending the night in Tallahassee. So, I just don't know which 2 days it is. They were supposed to have the paperwork ready for me yesterday. They didn't. So, I'll find out tomorrow. Okay, for sure, which 2 days. May be able to find out sooner, but so anyway, I don't know which 2 days it is. If it's Tuesday that I'm going to be out of town, then what I'll have ready for you either this Thursday or next Tuesday, I'll have the lab ready. We'll either do it Thursday or I'll have it ready for you for Tuesday. The test for chapter 8, because we will finish sometime on Thursday, and then the final exam. So I'll give you the option of doing that. If I'm out of town, you can take them all 3, or you can take 1 or 2 of those things and wait and do the other 1 or 2 or 3 on Thursday when I'm back in town. But if you want to go and knock them out on Tuesday, you can. I'll have somebody up here with all that, and I'll return all your papers. So I'm asking you, please, get me anything that you're behind in this week if possible, so I can return them to you as soon as possible. Okay? Okay. Now, if I'm in town on Tuesday and going to be away on Thursday, then I'll be here and administer all that stuff and wrap up the term on Tuesday. If I'm not here, then you have the option of either doing it with the person who's here or coming back Thursday, and then I'll be here and we'll wrap it up that way. So that's how we're going to end the term, uncertainly. But I should know by Thursday. Okay, so we'll know. All right. But you know your test on Chapter 6 is Thursday, and the test on Chapter 8 and your final exam will either be Tuesday or Thursday of next week. And the lab will either be Thursday or Tuesday. Thursday of this week or Tuesday of next week for Chapter 8. There's only one lab there. So here's Millikan's oil drop experiment. Here's the oil sprayer, atomizer they call it, spraying little, tiny little droplets, tiny little droplets of oil. And here's a charged plate. Positive on top, negative on bottom. That's important. Okay? And the droplets, most of them played out on top. They don't even go through, but there's a little bitty hole there. And some of those droplets actually fall through that hole. And now they're under the force due to gravity. Okay? And that's what's pulling them down. Okay? Now, if there's no charge here, they all fall at the same rate. Remember, acceleration due to gravity is the same for every object, right? But these are charged, so some of them pick up electrons, and if they pick up an electron, then there's a electrostatic force that's pulling them toward the positive plate, repelling them from the negative plate, but gravity's still trying to pull them down. And by studying, I have a little viewing scope here with calibrations on it, so you can measure how far and how fast they're moving and determine how much charge they picked up, or at least multiples of that charge. And the least common multiple of that will be your electronic charge. And that's how Millikan determined the electronic charge. Now, what I was going to say, I started to say it earlier, when I went back to grad school at Georgia Tech, after I got out of the Navy, I needed 12 hours to be a full-time student to get my full GI Bill. So I found 2 physics courses I could take, and, thank you, then found a math course I could take. I needed one more and found this physics lab. That's all it was called, physics lab. So I decided to take it, okay? And we got to do Millikan's oil drop experiment in that lab. And it was pretty nifty to watch those droplets falling and then stop and start, some of them going up, some of them slow down. But all depended on how much charge they picked up. And by measuring those and the calibration rating that we had in the view scope here, you could, how many millimeters they had fallen, how long it took. You had a stopwatch and you timed them, and you could determine based on the acceleration due to gravity and how much they moved or stopped or whatever, you could estimate the charge on the electron. And we did, and came out not super good, but within 15-20% if my memory's right. Okay, so what did that do? Thompson had come up, J.J. Thompson had come up with the charge to mass ratio. This was a looks like a very large number, 1.7584 times 10 to the 11th coulombs per kilogram, charge to mass ratio. Now, frankly, yeah, 1.7584 times 10 to the 11th coulombs per kilogram. Well, guess what? A kilogram is a huge amount of mass. Huge amount of mass. So certainly it would have a lot of charges if you had that much electron. You never have that much electron. Okay? Millikan's result came up with a charge number. 1.60 times 10 to the minus 19 coulombs per electron. So if you plug that in, you know the charge. You don't know the mass. You know this charge to mass ratio is this. So plug in the charge up here, solve for M, and you get Q, which is 1.60 times 10 to the minus 19 divided by this ratio, 1.7584 times 10 to the 11th, and you get an incredibly small number. 9.11 times 10 to the minus 31 kilograms. What? That would be point. Zero. Yeah. Point. I think it's point 0.00000000000. 10 of those groups of zeros, 911. Before you got that's how many kilograms. That is an incredibly small number. You'll never measure that on any scale they've ever developed so far. I don't think they ever will. But this is how you got that mass by calculation. Okay. Now, not making too much progress here. Before we move on too fast, though, which we're not doing, discovery of the electron, there's a case study here named after the English physician William Crookes around 1870. The Crookes tube was an experimental electrical discharge tube used in early studies of electricity. You can read that if you want to. But there you have one person, William Crookes. You read on a little further, you get Michael Faraday. We'll talk about him a little bit later. We get cathode rays. You can look on that. J.J. Thomson, we've mentioned, okay, over and over. And then the case study on the oil drop experiment, as we've seen already, that's Robert Millikan. So in this chapter alone, there are so many people and experiments and concepts brought up. There are tons of paper topics right here, okay? And then there's some conclusions that Thomson came up with, 4 listed, and then Millikan came up with 3 more. And they were all pretty much covered in that last slide. All right. Early models of the atom. Okay? Dalton said atoms are indivisible. Thomson and Millikan's experiment showed that electrons, the mass incredibly small, no measurable volume at all, okay? That's a negative charge. Where are the positive charges? Okay? Well, J.J. Thomson had this kind of a model. Again, these are just models, okay? And he said plum pudding. He was from Britain. This is, I guess, something they like to eat there. It was a pudding-like structure that had raisins or currants or something that mixed around them. So he figured that. The electrons were embedded in a blob, that was no better word, of positively charged matter like raisins in a plum pudding. The best I can come up with is my wife makes a really good, what is that called? Bread pudding. And, you know, it's mostly bread, but it has raisins and stuff scattered around in it. That's what I think of. I've never had a plum pudding, but that would be sort of equivalent to it. Okay? So positively charged matter, the blob, and just the raisins are scattered throughout the blob. Hey, no one could tell what was in an atom. This was just an idea. It seemed to fit. Okay? But along came another guy, Ernest Rutherford, 1907. Oh, goodness, my leg hurts. Remember Millikan, 1906? Ernest Rutherford, 1907. This had to have been the height of chemistry. You know, I mean, when they were putting all this stuff together, these great minds were working in different countries and scattered around here. Ernest Rutherford came up with this concept. Okay? By now, they had discovered that there are things called alpha particles. Now, I'm not sure they knew exactly what an alpha particle is, but they knew how to generate them. And what an alpha particle is is 2 neutrons and 2 protons. That's all. So it's a positive charge, very small, but much more massive than electrons. So they could produce these alpha particles, put them in an electric field, and because they were charged, they were repelled by the positive side, attracted to the negative side, so you could fire these things off. Okay? Now, one really nice thing about gold, besides being valuable and looking pretty and stuff, gold is extremely malleable, meaning you can roll out gold in as thin a sheets as you can almost imagine. In fact, has anyone ever heard of gold foil? Okay, that is, picture aluminum foil but gold, but much, much thinner. And actually, this is what a lot of picture frames do. If you've seen these look like gold picture frames, they're really wood picture frames, and someone's taken gold foil and put over it and rubbed it into the wood, and it sticks in the wood, and it looks like the whole frame is gold. It really is wood, and that foil is in there. So he had gold foil, very, very, very thin gold foil. Now, on average, I think this was no more than a few molecules thick, okay? It's that thin, okay? Had this very thin gold foil. He scattered the alpha particles off of this foil. Now, if Thomson's plum pudding model was valid, these positive charges would have been repelled off most of this gold foil. Okay? Right? Okay? Because if that's what the atoms look like. What he found out, surprisingly, most of them pass through without any significant deflection at all. So how in the world do these positive charges go right through Thomson's plum pudding? The answer is they couldn't. Okay? Second? Oh, okay. They couldn't possibly. So therefore, the model was wrong. Now, what he did find that some of these alpha particles deflected almost directly backward. Very few, but scattered. Most of them went straight through without encountering any resistance. Others were scattered back, and then a few at various other angles. So the conclusion was the atom's positive charge did not reside in a blob of pudding, okay, but was very, very small, but incredibly massive nuclei. And that's what these few alpha particles were bouncing off and bouncing way back, okay? But most of the rest went right through without encountering anything. So the conclusion is the atom's positive charge resides in a very incredibly small but incredibly massive, that sounds like it's contradictory, but it's not. Small volume, huge mass, nucleus. Later, the positive charges were identified as protons, and then 30 years later, 25 years later, finally James Chadwick, here's another name, he also discovered that neutral neutrons were also in the nucleus. Okay? So it took a long time because neutrons are really hard to isolate. They have no charge, very tiny mass, I mean large relative to other things, but still very tiny, very difficult to isolate. But he was able to discover them. James Chadwick. Okay? Here's a picture of Rutherford saying, here's your radioactive alpha source. And you might think, wasn't this dangerous? Yeah, maybe a little bit, but not too bad. Alpha particles, if you had a piece of paper here, you would block every alpha particle that was trying to hit your skin, just with flimsy paper. So they weren't super dangerous. I'm not sure they realized that they could be somewhat dangerous. But most of these radioactive alpha particles went right through the gold foil and hit back here. Okay? A few, not too many, got deflected a little bit, but several of them got deflected way, way back. Okay? And that meant that most of the volume of the gold here, there was absolutely nothing there. Nothing there. Most, and this, I think I've said this before, when my older brother came home from college. I was still in high school. He came home from college. He had his first physics class, had a really good professor, and he came home and explained what he had learned, and he said, most of everything is nothing, okay? Even lead, gold, these really heavy things, most of the mass is isolated in these tiny, tiny little nuclei that contain almost all the mass. And then you have a cloud, a huge cloud of electrons that takes up all the volume. The electrons have almost no mass, and there are not that many of them, so most of everything is totally empty space. Most of everything is nothing. Okay? Nothing there. And this is what Rutherford found. Okay? His gold foil experiment. Here's an illustration of that. Let's just say that that gold foil was so thin that it was no more than 3 atomic layers thick. It was probably much bigger than that, but let's just say this, okay? You have a tiny little nucleus, and this picture has the nucleus way too big, by the way. It would be a little pixel, but you wouldn't be able to see it, so it's a tiny nucleus, and this is the electron cloud around it. And gold is a really dense metal, really heavy metal, okay? But most of these alpha particles, since they're positively charged, they don't even come close to those nuclei. So most of those go right through. But occasionally you'll have one that'll hit right on the nucleus and bounce back either up here or back here or somewhere else. So every now and then you'll have a deflected one, but the vast majority goes straight through without ever deflecting at all. Okay? That's what, and if this was really plum pudding, most of them would have been deflected. All your alpha particles would have wound up back here. As it turned out, most of them wound up over there. There was nothing to get in the way. Only those tiny little nuclei would deflect them. And that's what Ernest Rutherford discovered. He wasn't looking for that. It was quite a shock and surprise to him that that was the case. Okay. Here we have, find you in a minute, Joseph. All right. Well, we're going to build up to almost a full class. Who are we missing? Bailey and Teff. I think that's the only 2 we're missing. Well, we've lost a few. Okay. But hopefully some of those will be coming back. Okay. So there's the nucleus based on Ernest Rutherford's experiment with gold foil and alpha particles. So what does this lead to? The nuclear atom. All right. Here's how we classify various atoms. And if you want to find your periodic table, it's either on the back page of your book, if you have one of the big books, or it's somewhere later on in chapter 8, just a few pages from where you are now. Every different element has its unique number of protons. This is what makes an element an element. Hydrogen has 1 proton. That's all, folks, 1 proton. Helium has 2. Lithium has 3. Beryllium has 4. I want to say carbon, but I think it's boron. Boron has 5. Carbon has 6. Nitrogen has 7. Oxygen has 8. Fluorine has 9. Neon has 10. Sodium has 11, magnesium, you can go on down, write down the periodic table, and every element has a unique number of protons. And you have to get up way into the 100 and some before you start skipping some. They think there's some others out there, but they haven't discovered them yet, okay? But this is what makes an element an element. And that's why protons are never exchanged. if they lost or gained protons, they'd become different elements. They don't do that, okay? So charge exchange only comes in the electrons, not in the protons. So the elements are distinguished by this atomic number. Give me an atomic number, any number in the world between 0 and 100. 26. Is that what I heard? Okay, 26. You just picked out iron, okay? That's the only element that has 26 protons, ever. And iron will always have 26 protons. Always, okay? So the elements are distinguished by their atomic number. Now they say in this slide, 113 elements have been identified. Since this is an old slide, they may have a few more by now. On the periodic table that's in your book, you'll see some of them are UUNs or things like that. That means they haven't identified them yet. Okay? 113 elements identified. Now some of these last for a microsecond in radioactive reactions and then disappear. So some of these are very unstable. Now, the number of protons has to equal the number of electrons if you have a neutral atom. Because the protons are all positive, electrons all negative. For it to be a neutral atom, if it has 26 protons, it's got to have 26 electrons to be neutral iron. Okay? Now, of course, they don't have to be neutral. You could have positive, excess positive charge. That means they've lost some electrons. Or excess negative charge. That means they gained electrons. You never gain or lose protons. That would be a nuclear reaction. We don't do those. Only electrons get it. Then they would be ions. If they're charged, they're ions. If they're neutral, they're atoms. Okay? Now, have you ever heard of the term isotope? The prefix iso means the same. An isobar is a line of equal barometric pressure. You'll see these on weather maps. Okay, either centered in a low pressure system or high pressure center. Those sort of shapes around that would be isobars. If you did topographic map, they call them isoclines, lines of equal elevation. If you're going up a mountain, there would be everything at 100 feet above the base, 200 feet, 300 feet, they would make isoclines. Okay? Well, this is iso. Something is the same. Same atoms, but different atomic masses. Well, you see, the same number of protons. To be the same element, you've got to have the same protons, always. But if you have different number of neutrons, these make your isotopes. Same elements, but slightly, ever so slightly different atomic masses. Why? Because the neutrons have no charge. And generally the number of neutrons can vary. Sometimes if there's too many, they're radioactively unstable. Okay? Maybe if there are too few, they're radioactively unstable. But most of the time they can gain or lose a few neutrons without hurting anything. Okay? Not usually too many. So here's an example. Hydrogen. Every hydrogen atom has a single proton. Okay? Most hydrogen atoms don't have any neutrons at all. 0 neutrons. Just a single proton. Okay? So its atomic mass is 1 and its atomic number is 1. Atomic number on the lower left, atomic mass on the upper left. However, every now and then, maybe once every 100 hydrogen atoms you'd ever run across, maybe less frequently than that, you'll have one that does have a neutron. So now it's still atomic number is still 1, that one proton. Now the 2 represents an additional mass, which is from a neutron. Now because that's twice as heavy, but it's the same hydrogen, we call it deuterium. That was the old name for it, deuterium. So this is the atomic number on the lower left, mass number on the upper left. Okay? But about 1 every 10,000 or so, you'll actually have a hydrogen atom with 2 neutrons. It's still hydrogen. It's got 1 proton. That's anything 1 proton. But it's 3 times as massive as the other. It's called tritium. Very, very rare. Okay? Now, why do we mess with hydrogen? Because adding a single neutron doubles its mass. I mean, that's a pretty big increase. Adding 2 triples the mass, okay, because you only got 1 proton to be hydrogen. So it's really easy to detect these. They're very rare, but it's easy to detect. How we usually detect them is what we call heavy water. Okay? Now, there's several reasons for this, and this is just one minor reason. But where do you find nuclear power plants being? Every nuclear power plant you've ever heard about, where was it? Near water. You're absolutely right. Generally along a river. In Japan, they actually had some right on the seashore, so they were close to the ocean. Now, there's 2 reasons to have it near water. Because in a nuclear reaction, enormous amounts of heat are being given off, and you use water to cool, okay? But you also use water to turn the steam, to turn your turbine. That's the whole purpose of having a nuclear power plant. But the other reason is they like to isolate these heavy hydrogens, okay? Because these extra neutrons help absorb excess radioactivity. And that's how you control the radiation in the radioactivity, the what we call it, chain reactions that are going on in the nuclear power plant. If things start getting too hot, overdoing, they put these tubes of heavy water in, these extra neutrons absorb that energy and bring it back down. That's called scaling or protecting that. And what happened when Chernobyl, we talked about that, didn't we? In Ukraine, 3 Mile Island, somewhere in New York, Pennsylvania, somewhere up there, island in a river, okay? Or Fukushima, I think was the name of it, in Japan, when they had the earthquake. When those got out of control, Fukushima, I know because the tidal wave knocked out power, okay? When it knocked out power, they couldn't, operate the machinery anymore, and the thing started overheating. They did get it shut down before any major thing happened, but it released an awful lot of radiation, okay? We're talking about Chernobyl went completely out of control. 3 Mile Island, they did a pretty good job of containing that, but it was in the process of going out of control. So this is how we name our elements. Put the symbol for the element here, the atomic number, which is number of what? Atomic number gives you the number of protons, and the mass is the sum of the protons and neutrons. Okay, the sum of the protons and neutrons. Okay. I wish they did something other than hydrogen, because that's what they always do. Okay, so like we just said, the mass number is the sum of the number of protons and neutrons. Now, back when I was taking chemistry in high school and freshman in college, they called these AMUs, atomic mass units. Nowadays, they just call them U's, units, okay? But it's atomic mass units, but they just shorten it to U. And basically, this is 1/12 of the carbon-12 isotope mass, okay? Seems a little redundant and circular in the reason, but there's a reason they do that. That's how many AMUs you have, or U's you have. The 1/12 of the carbon-12 isotope mass, okay? Now, the atomic weight is the atomic mass of an element averaged over the naturally occurring isotopes. If you have more than one isotope, and most elements do have more than one isotope. Hydrogen has 3. Hydrogen, deuterium, and tritium. Okay? Most of them have more than one. But most of hydrogen's isotopes are the pure hydrogen, single proton. Just very rarely will you find the deuterium, and way rarely will you find the tritium. So most of them are going to be those naturally occurring hydrogens, just plain hydrogen. Okay? All the other elements are pretty much the same way. They'll usually have one dominant isotope and a few every now and then with one or two extra neutrons, or one or two deficit neutrons. Okay? Now, here they show hydrogen again. I don't know why. I would have picked out something else. Same slide we saw before. The atomic numbers here, which is, what does that measure? Protons, and the mass number? Proton plus neutrons. And you'll be doing that in lab, by the way, when we do this lab. All right. Now, here is nitrogen. Okay. Nitrogen has two major isotopes. Okay? 99.63% of the time, that nitrogen is going to have what? 7 protons and, yes, and what would that be? 14 sum of neutrons and protons, but if you know it has 7 protons, 7 neutrons, okay? Most nitrogen, 99.63% of the nitrogen in this room, and most of the atoms in this room are nitrogen in the air. Most of them are nitrogen, about 80% of them are nitrogen. 99.63% of them are 714 nitrogen, okay? However, 1 out of every 300 or so will be, what's the difference? That's a 15 up here, a 7 down here.
There'll be one more neutron.
One more neutron, okay? Be just a little more massive. Hardly noticeable, but a little more massive. But it'll have 8 neutrons, not 7. Okay? Still nitrogen, still acts like nitrogen, no change, except that it's a little bit heavier. Okay? So, this has, what is its atomic mass unit? Very close to 14. Not quite exactly 14 because it's all based on carbon-12. So 14.00307 units, atomic mass units. Whereas this one has 15.00011 AMU. That's almost 14 and 15 on the nose. You know, 4 decimal places, it's that on the nose. 5 decimal places, it's that on the nose. Okay? So, well, 4. Okay? But you multiply its atomic mass times its frequency, 0.9963, move this stuff in 2 places this way, multiply this one, 15, by 0.0037, and add those together, and you come up with a little more. So you see this changes that just a little bit. The 5th decimal place, or 5th significant digit, it changes it by 3. Okay? It doesn't average these two. It weights them according to what the provenance is. So most of the time you have one dominant and some that are very, very minor. Okay? Okay. So the atomic weight is the atomic mass of the element averaged over naturally occurring isotopes, depending on what the mass of those isotopes and the prevalence of those isotopes. So if you just take a quick look at your periodic table, now they don't put the numbers in the same places, but if you look at it very carefully, you'll see. Okay? Here's hydrogen with 1. That means it's proton numbers, mass atomic numbers. Okay? Then it's 1.008. That means 8 out of every 1,000 will be a little bit heavier. Okay? Meaning deuterium probably. Helium, 4.003. 3 out of every 1,000 might have an extra neutron. Most of those have 2 protons and 2 neutrons. lithium, 3 and 3, but, oh, I'm sorry, 3 and 4 generally, because that's closer to 7 than it is to 6. So the dominant lithium has 4 neutrons, but occasionally you have one with only 3. Okay? Beryllium is usually 5 neutrons to 4 protons. Boron is generally 6 neutrons to 5 protons. Carbon is 6 to 6. Nitrogen 7 to 7 most of the time. Oxygen 8 and 8. Fluorine 9 protons, 10 neutrons. So you look at this, and then wherever the decimal point is, you know whether it's going to be a little lighter or a little heavier, depending on what your dominant one is. Go down to chlorine. That's a pretty obvious one. Chlorine is 35.45. That's almost 35 and a half. That means the dominant one is 18 neutrons, but almost as many will be 19 neutrons, but not quite as many. So maybe 52% to 48%. So it has 2 that are almost equally dominant. All right, so that's what we mean by the atomic weight. So that's why they're never whole numbers, or hardly ever. The 2 decimal places, a couple of them, like oxygen and fluorine, are very close to whole numbers. But because they have some zeros there, it indicates somewhere out there you probably do run into another decimal place that's not 0. Okay. Probably way more than what you're interested in, but there it is. So let's look at what they call the classical atom. Okay? Now, by this time, we've made it over to page 210, and at the top of the page is a case study on early Greek philosophers on discovery of the nucleus, and this takes it from J.J. Thomson to Ernest Rutherford. So there you have more about those 2 guys. Okay? Now, this is sort of a interlude here. Basically, where we are here is right around the turn of the 20th century, beginning of the 20th century, right around 1900, when all this stuff was being discovered. Remember, late 1800s was J.J. Thomson, wasn't it? Or was he 1906? And Rutherford 19. I mean, they all came right about the same time. They were finding all these new things out about how matter was structured, and it was just incredible. Well, by the classical atoms, here would be the predictions of classical theory. And when you say this, we almost mean Newtonian physics, that physics that Newton came up with that deals with the macroscopic world. Okay? We know that electrons now go around the nucleus. After Ernest Rutherford, we knew that electrons had to be in this cloud that orbits the nucleus. Now, because they had a curved path, they weren't flying out, you had to have an acceleration. You know, there has to be a force, centrifugal force, pulling them in. So they had to have an acceleration. Usually, when you accelerate charges, they radiate. They give off energy. We knew that, okay? If the electrons are giving off energy, then they're losing energy. If they're losing energy, then they're ultimately going to spiral into the nucleus. If they spiraled into the nucleus, they would collapse on themselves, and atoms couldn't exist. Wait a minute, we know atoms exist. This is what classical theory tells us, and it can't be true. What's going on here? Well, they did experiments and say, hey, guess what? Atoms do exist. That's not really an experiment. They knew that. You needed a new theory. Now, along about this time, the physicists were sitting back on their laurels here and said, look at all we've discovered. Okay? The chemists, they still have some work to do. Biology, boy, they have a lot of work to do. All these other fields, they have plenty to work on. We've almost tied up our entire scientific field in a neat little package. We understand just about everything that's going on. We're missing just a few little details here, like this. We know that can't be true. There has to be something else here. So we just need to work on this couple little details here. We're going to have it knocked. From now on, we just figure out ways to teach this and new things we can do with it. We've got it knocked. We've almost got it all figured out. We just need a little bit of a tweaking to our theory to make sure this doesn't happen, because we know it doesn't. Well, guess what? That little bit of tweaking led to quantum mechanics, dividing atoms, nuclear energy, nuclear power. Yuck, everything got blown up. They realized after a while, they knew so little of physics that there was worlds of physics beyond what they thought they knew. So here's the quantum concept. Okay? And this started right about the turn of the century. Max Planck, a great German physicist. In fact, some of the premier universities in Europe, they're in Germany, but they're all over Europe, are Max Planck Institutes. Now, two ways I learned about these. One, we have some very good German friends in town. We're the godparents for their boy, and really close to their daughter as well. We were sort of host families to the woman when she was over here on the Fulbright scholarship before they were married. In fact, she hadn't even met her husband, and then they moved here after they married, and both kids have been born since they've been here. So we've been with their family a long time, close to them. We traveled to Munich several times, and every time we do, we go and stay with Olaf's parents. In fact, one trip we made, we flew into Frankfurt. My wife had professional meetings in Nuremberg, but the best flights she got were in Frankfurt, and we planned to take the train from Frankfurt to Nuremberg. Well, when Miriam found out about this, she contacted her mom, who lived near Frankfurt, and her mom picked us up at the airport and drove us to Nuremberg, stopping along the way, telling us where Miriam went to college, and showing us these neat towns. So we had a German guide through much of central Germany, okay? Great trip, okay? We got to Nuremberg, and Karen had her meetings. I got to tour around the city. They had a really good time doing that. And when the meetings were over, Olaf's parents drove up from Munich and picked us up at the hotel and drove us back to Munich, touring us around, showing them where they went to grad school and various things like this in some of the historic areas. So we got a real good thing. Well, long story short, Olaf's father worked at Max Planck Institute in Munich, okay? One of the institutes in Munich. So we got familiar with it that way. We also had, several years before, some really close Italian friends. We found out later they had gotten married just a few months after we had. Of course, they were in Italy, we were in Atlanta, but when we got married. But when they came over, Fabio was working on his degree at the same time my wife Karen was, and they were just really close friends, and so Rita and I got to know each other as well. So we met, and after Fabio graduated, he got a job with a pharmaceutical company up in Boston. So they moved up there, and while they were living there for about a year or two, his son was born. So his son was actually born in the U.S., so he was actually a U.S. citizen. Well, after a few years there, they moved back to Italy. Fabio's parents wanted them back there to take care of them, this kind of stuff. So they moved back to Italy. The two daughters were born there. And we hadn't met any of the kids. And then Fabio had a chance to come back and do a postdoc at UAV again. And now the kids were in junior high, grammar, upper grammar, lower grammar, pre-K, something like that school. And we got to know the kids too. Well, then later we went back. Karen had meetings in Rome, and we took a train over to Trieste and met with them there. And the kids were high school or junior high type age. And we really got along well with Giacomo, who was a boy born in the U.S., U.S. citizen. He was very, very bright, just like his dad. Well, like I said, he was in high school, and his parents wanted him to have the opportunity to come to school in the U.S. since he was a U.S. citizen. But they figured that his chances would be greater if he came to a U.S. high school. So they were looking to find a place for him to do boarding school. And happened then when they saw how well we got along with him, he was a delightful kid, they started looking at Birmingham, found a school for him, and asked if he could live with us. So he came and lived his senior year with us in Birmingham. Went to Altamont High School. I don't know if y'all know of that. It's a small private school, but pretty good. And then he went back to Italy, and in Italy they have 5 years in high school. So he graduated in U.S., and he went back to Italy and graduated with his class in the Italian high school in Trieste. So then he had an opportunity that year to come back, and we took him around to see different colleges because we were sort of like his parents here. And he got offered a full ride scholarship at University of North Carolina. We're out at a good school, that kind of stuff. But he also got accepted at Harvard. And because he had been born in Boston and his mother loved Boston and Harvard, he wanted to go to Harvard, where they had the Ivy, the old buildings and all this stuff that he thought was so cool. So he wound up going to Harvard, costing his parents a fortune and a half, I think. I think they actually lost their home because they moved into an apartment so they could pay for his schooling at Harvard. And then when he finished there, and he did quite well there, he decided to do grad work. And guess where he is? Max Planck Institute in Munich. Okay, he was at the one in Grenoble where they have the accelerator, and he did a lot of research there. He's finishing up at Max Planck. So we know about it in two different areas. So he came along and he introduced this idea that the energy was not broad spectrum energy, but all energy of things like light and other things was quantized, meaning it didn't come as a spectrum, it came in unique little packets. And these were called photons. Light specifically was called a photon. And this is Planck's constant, 6.63 times 10 to the minus 34 joule seconds, which is an incredibly small constant, times the frequency, the photon frequency, the light coming out of that, each frequency of light has a certain frequency, multiply that, and you get the energy. And these energies are very small differences, but they are quantized packets of energy. 5 years later, boy, mentioned all the great chemists that were around this time. Look at the physicists that were. Max Planck, Einstein. He said that light was made up of these quantized photons that Planck had introduced this concept. Planck's constant was there. Einstein came up with this, and he based this on what was called the photoelectric effect, that certain photons are emitted when light, in other words, or packets of energy, when light hits a certain substance, the photoelectric effect. Okay. The higher the frequency protons, the more energized those protons were. And we know this to be the case. Think about our visible light spectrum. It goes from red to violet. Okay? Below red is infrared, that's just heat. Okay? Above violet is ultraviolet. That's the stuff that causes skin cancers and cataracts and things like that. Also causes tanning and those kinds of things we talked about, which is actually damaging skin. Okay? So the higher the energy, the higher the frequency, the higher the energy, the more damage it does. Thankfully, our atmosphere screens out most of the ultraviolet. Some gets through, and it screens out almost all of the X-rays and other very high energy photons that would actually kill us, do major damage to our system. We're really fragile little beings, and our atmosphere protects us. So, how do we know this kind of stuff is true? And this is what I was kind of referring to before. We have these, what they call atomic spectra. Everything, all things emit radiation. And this is sometimes called black body radiation. Things absorb radiation, emit radiation. It's continuous radiation distribution. You don't see these individual packets. However, this black body radiation depends on the temperature of the radiating object, which would indicate there's energy dependence here. If you break it down into the individual frequencies, you can see that the characteristics of solids, liquids, and dense gases, you can distinguish this by the amount of black body radiation. Okay? Now, if you break this down into finer detail, you'll see line spectra. Okay? Now, this first, it's not going to show black body radiation, but let's say that we had a light bulb here. Now, inside that light bulb is probably a tungsten filament. The tungsten filament emits certain frequencies of light. Okay? Now, send that through a slit, a very, very narrow slit, so you don't have interference from others, and you have a single band of these light rays or particles. Okay, we haven't gotten there yet, but coming through that slit, send it into a prism, and because of the difference in the index of refraction of air, index refraction of the glass or the material the prism is made of, it splits that up. And then when it hits the other wall, it splits it even further, and that's where you get your spectrum. Red, orange, yellow, green, blue, indigo, and violet. Okay? They leave off the indigo. If you put in indigo, you get Roy G. Biv, which is just a way to remember it. Indigo is something between blue and violet, just to have a vowel in there. Okay? But this gives off that spectrum. Now, sunlight would be slightly different. Different lasers that you might have here would be very distinctly different. Okay? But these are emissions and characteristics. Okay. So this is almost more like black body. Here would be the individual line. Let's say we had a tube like a neon tube or some very specific gas here into this, send it through the slit, and rather than a continuous spectrum, you have individual lines. Orange line, a blue line, a violet line, and whatever that is. Okay, that would be your line spectrum. That's if you had a pure material here, you don't have the mixture of all the and the continuum you have. Diffuse matter. This is really a bad slide here. Diffuse matter creates incandescent gases. That's a weird way to express something. If you have incandescent gases, you get diffuse matter. That would be the better way. Illustration are the Balmer series of hydrogen lines. Let's see if we can get that. No, we can't. Okay. Well, maybe that is supposed to be that. Let me see. All right. I don't think we're going to have time to go into Balmer series. Before we leave, though, I should have picked up on this. Let's do this one. Oops, we can't do it. We're going to use Planck's law here in example 8.1 and 8.2. Let's do them real quickly. What is the energy? So we're looking for E. Whoops, I need to get my pen, my color done. What is the energy? So we're looking for E. That's the unknown here. Of a photon of red light with a frequency for red light of 4.60 times 10 to the 14 hertz. Does anyone know what the unit hertz is? It's per second, 1 over second. That's what a hertz is. Cycles per second is really what it stands for. But a cycle isn't really a unit. Okay, how would we find this? What was Planck's law? There it is. E is equal to HF. Okay? So E is equal to HF, where H is, let's go back here and get H, 6.63 times 10 to the minus 34 joule seconds. So this is 6.63 times 10 to the minus 34 joule second. Okay? So let's plug that in. 6.63 times 10 to the minus 34 joule second, as a multiply, times 4.60 times 10 to the 14 hertz. Now what's a hertz? It's a per second. Okay? Per second. This cycles per second. Well, this second is going to cancel out that one, and you get energy in joules. So if someone has a calculator, you have to use your scientific notation button, which is EE or EXP, 6.13, EE or EXP, negative 34, and that negative is the negative sign in parentheses, not the subtraction negative, times 4.6, EE 14, and you're going to come up with a number that's on the neighborhood of 10 to the minus 20, maybe 10 to the minus 19, 10 to the minus 20, something along there. What do you get? 2 point something or 3 point something? Anyone do it? Got a calculator? Nobody? Nobody has a calculator. Well, we'll have to use their word for it. That is, they get 3.05. I thought it was somewhere so in that neighborhood, times 10 to the minus 19, and the unit is joules. Now that seems like a tiny amount of energy, but if you think about it, look how tiny H is, and you know how many hertz you got. It's not an unreasonable thing for a single energy level for that type of gas. Okay, 8.2. What is the energy of photons of violet light? So it's going to be the same formula. The H is 6.13 times 10 to the minus 34 joule seconds times, and violet light is 7.30, the frequency, times 10 to the positive 14 hertz, which is per second. This second cancels out the per second. And again, you're going to be in the neighborhood of 10 to the minus 19, but this number is going to be quite a bit bigger, like 4 something another. They get 4.84 times 10 to the minus 19. So they're close, but definitely a difference here. 3.05 to 4.84. Both of them times 10 to the minus 19 joules, but definitely higher energy in violet than you have in red. Okay? And if you think ultraviolet, then it's higher energy. That little bit of difference there damages your skin, causes cataracts, causes cancer. Whereas down there around the red range, yeah, you won't get anything like that. You get heat in infrared, but you know that doesn't bother you. I mean, it might make you uncomfortable, but it doesn't damage tissue. All right, so where we're leaving off then is, yeah, I didn't know we were on boards there. So we're on page, there is another exercise there. I think what we'll do is wait and do that one next time. We'll start with example 8.3 next time. Well, wait a minute. Let's back up. We're going to start with the Balmer series. I knew that was in here. And the Balmer series is right there on page 212. Swiss mathematics teacher named J.J. Balmer was studying regularly, blah, 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 we'll talk about the bomber series, and that's what this last little bullet here will involve 8.3. Okay, then we'll get into Bohr's theory. Okay, just to get an idea, you know, there is a chance that we'll finish Chapter 8 on Thursday. We'll shoot for it, and if we do, we'll, well, whatever we do, we'll either be ready for, we're going to have the test on Chapter 6 Thursday. We may have time for the lab on Chapter 8 or not. If we don't have time for it, we'll do it on Tuesday. Whether I'm here or not, someone will be here. Just pass out the paper lab, you use the chapter, work it out, okay? And you can work among yourselves. And you'll also do the test on Chapter 8 on next Tuesday. Whether I'm here or not, someone will be here to administer that to you, and then the final exam. If you choose to take it, if I'm not here on Tuesday, I'll be back on Thursday. So, I'll be here so you can take the final then if you choose not to take it on Tuesday. But if I am here on Tuesday, then we probably pretty much, that means I'll be away on Thursday. That means pretty much we'll have to get everything wrapped up on Tuesday. Will that be okay?
Yeah.
All right. We'll work it out there. So we're going to move to lab. I left the lab being copied. I haven't had a chance to go down and pick it up. You can go into the lab. We're going to be in there. Thank you.
I need the one from next week.
Okay. I'll pass those out when we get to the lab. Okay.
Last Thursday.
Okay, I'll pass out when we get to the lab. Doing pretty well, thanks. How about you? All right, we're starting what I think is Lab 11 on electromagnetism. Now, on your sheets I just gave you, you'll notice Roman numeral 1 is answer any 12 or more even number conceptual questions. Don't do that. That's the previous text. We're not doing that anymore. But what we are doing is experiments dealing with electromagnetism. I'm going to give several of you some strips of metal here. These are all elements. I can't read. Okay. Okay. Who wants one? You're aluminum. Okay. You'll be copper.
Yeah.
Two. Okay. You want iron? Okay. You want lead? Okay. You'll be lead. Nickel. Okay. There's a nickel. Tin.
This man right here.
Okay. Ring tin. Okay. And zinc.
Over here.
All right. Here's the zinc. Okay. Now we have a few more pieces if anyone really wants one. There's plastic, wood, and styrofoam. Plastic, wood, styrofoam. Did I hear someone say I would? Okay, never mind. Okay. And styrofoam? You already got one. Okay, your styrofoam. Oh, you already got one too. Okay. Now, some of these are pretty obvious, I think. So what I want you to do, aluminum, come forward. And you'll see here on this electron magnetism master, here's a magnet here. So you put on either side of that, see if your aluminum's safe. Now before you do, aluminum's a metal. Aluminum is a fairly decent conductor of electricity, so you think it'll stick or not?
No.
Try it. To either side. No, up here. Got any attraction? No, too bad. Give it back. Okay. All right. Who's copper? Okay, here's copper. Copper's a very good conductor. Yeah, you'd be right no for aluminum. Copper? Okay, try it and see. Uh-oh. No, that's not. You lose it too. Okay. Copper was a no. Okay, iron? Who's our iron guy? Iron Man. Oh, there. Okay. Well, next, what do you think? Not a very good conductor. Stick this here. Oh, what do you think? It does stick. So this is, after all, a magnet. So iron's a yes. Okay, turn it in. Okay. Who is lead? Aren't you lead? Oh, you swap. A very heavy metal here. What do you think? Here's the magnet either side. Nope. Lead is a no. Okay. How about nickel? Nickel's a nice shiny metal. What you think? Yay or nay? Yay! Look at that. It sticks. Good deal. Thank you. Okay. So lead is a yes. How about tin? I mean, nickel's a yes. I'm sorry. Nickel's a yes. How about tin? Yeah, either side. No, not top. Either side. No, here or here. Here or here. Okay. What you get? Nothing. Okay. Tin is a no. And how about zinc? No, zinc. Okay, here's zinc. Either side there? No, nothing. Okay, good deal. Okay, how about plastic? Yeah, I think I know this one. Nope, no plastic either. Okay, how about wood? The wood? Okay, there's wood. What do you think? No way. Okay. All right, and styrofoam. I've seen styrofoam stick to stuff before. Is it magnetic? No. No. Okay, no. All right, here. You don't get to keep it. Okay. All right, so everybody got those done. 2A. All right, now, I didn't have a chance to do this beforehand, so y'all are going to be doing it now. Okay? I'm going to pass out to you a bunch of pins and needles. Okay? Huh? You don't have to start from the door. It's okay. Don't lose these. Yeah,
you already knew it.
Y'all get in there?
Trey.
Okay, not that kind of needle.
Trey.
Yeah, but that's what here. Yeah.
We got one already.
But a few people get to.
That's true.
I found that stuff on my
You got one. All right. Okay. Now, what I want you to do, if you got one or two, when I bring this around, stick it in the iron filings and see if. No. Okay. You got a few to stick. You got more, so this one's out. Hold on.
So mine was.
So far, yours went. Hold on to the end. So yours is out because yours is really yours may still be in. What down? Oh, yours really is. Yours is. Okay. Try your head too. Flip it over. Flip it over. Huh? So far, no.
You don't have to have a $400 window.
This is not.
You get the
Yours is leading so far.
and just like a little thing.
Now, if someone
What you sell them?
wipe it off.
Yeah.
You get 50% off tools that I got a whole bunch.
Oh, you're
When I first started my job, that's why I started with when I first started my job, first in the hospital.
okay.
Still in possible.
Oh, too much.
I know bullshit. That's too.
Probably had right that off. Okay, hang on. Wipe it off.
Some of them big ranches
Run off there.
Oh, you're trying to say who can pick up the lease?
Lease.
Oh.
do my job. He got so lucky one day. He found a bag of 3-inch ratchet, snap ratchet. He found it on the side of the road. I was using the battery, snap the battery. That day, I need a battery. Yeah, somebody left. I left a whole kit of tools on the back of the truck.
No.
It wasn't even mine. Yeah, I'm see all the way everywhere.
I had a special light where I do these little flat lights. And I can see anything.
He's got one more over here.
I hate losing tools, man. That actually
I
love myself too. I'll start taking pictures. Take a picture myself. So people come by.
Go back there and say, come over the plan.
Then you paint that shit. That's too much. Hey, that's how it. That's how it usually takes my job.
This iron power. I think there's still more than person. Okay. All right, throw it all around the house. Pretty clean. Yeah.
It wouldn't cry.
Hers was close. You're not magnetic. Oh, wait. Oh, you didn't get one. Okay. Did anyone end up with one besides? You had one, didn't you? Okay. Again, I didn't check. Everybody see. Okay? Y'all see that this picks up very few filings. Okay, it's slightly magnetic, but not super. Okay, like cloth here. I'll make it do this figure. Flip it over and do the head. Well, I have a few. Surprising. All right, so this is about like several of the others, but this is very little magnetized. Okay, so if you want. No. Okay. What we'll do. All right, what we have to do, several pins have been placed, okay? This is B1. Test to see if it is magnetized by touching its point and head into the container of iron filings. If it is magnetized, place it in a container of water. Okay, not worried about that. What we are going to see is if you can find the pin, okay. What we're going to do, hers was slightly magnetized. We'll see if it's enough to make a compass needle move. If y'all want to come and watch this, you can. I'm having trouble getting this to point north. He is pointing north, but getting it to point up. There must be a lot of magnetic material in here, okay? You'll take the point of yours and hold it near the south or near the north. Okay. Take the point and point toward the north or point to the south. seems to be attracting the north-seeking pole, and it's repelling the south-seeking pole. So this is slightly magnetic. Okay? If I do the head, y'all want to watch this? Yeah. It's part of the thing. Okay? If I do the head, it's repelling the north and attracting the south. So this is slightly magnetic. Did everyone want to see that? Any of you just seeing it? Do it again. Okay? You see the compass is pointing basically north, or toward Justin, whichever. Okay? If I hold the point here, see the point is attracting the north-seeking pole and repelling the south-seeking pole. The head, on the other hand, is repelling the north-seeking pole and attracting the south-seeking pole. Okay? So that means, now the styrofoam has nothing to do with it. That's if I float it in water. Okay? And it's also to make it easier for me to pick up. Okay? So the question is, which is the north-seeking pole of the pen? The head was the north-seeking pole because it repelled the north. Okay. Yeah, the head is the north-seeking pole because it attracts the south-seeking pole of the compass. Okay. And it repels the north-seeking pole. Okay. So did y'all get that? B1, which was north-seeking pole, which was south-seeking pole of the pen. Okay. Now, it says if you can find a pen that is not magnetized, we couldn't, or at least weakly magnetized, and hers seemed to be the weakest, or one of the weakest anyway. What you want to do is stroke this magnet, the point, on a magnet. So I happen to have a magnet right over here. Okay, if someone wants to volunteer to stroke the point of this on the magnet. Anyone want to do that? Somebody, otherwise we're just going to eat some time here. And I'll be here till 6 anyway. Okay. All right, stroke this point. Stroke it. Yeah, on one side of the magnet. And do it in the same direction. Yeah, one direction. You're touching the magnet, right? Okay. Stroke it in one direction. One direction. Okay, now, what we want to do, good deal. Okay. Now, what we want to do is see if he increased the magnetism of the pen. Now, y'all saw how many filings he picked up before, right?
Yes.
Okay. What would you say?
Yes.
Yes, it did. Now, just to verify, did you stroke the point or the head? The point. Flip that over and put the head in here. Okay? Did that increase in magnetism? Yes. Now, how did that happen? He only stroked the point, but he magnetized both the point and the head. Okay? And magnets are always? Always? How many poles? Yes, they're always dipoles. Okay, if you magnetize one end, you automatically magnetize the other end. So number 2, B2, did you increase the magnetism on the head as well?
Yes.
Yes. Number 3, if yes, then explain how you increase the magnetism of the head by stroking only the point. Did you get it? Okay, that's number 3. Okay. Now, y'all indicated which was the north seeking and south seeking before. Who wants to check and see if that's changed or if it's the same? Okay, I've got all night. We'll stay as long as you want to. Okay, good deal. Okay. Now, again, hold the point toward either the north seeking or south seeking. What does it do? Attract or repel? Repelling that and attracting the north. So the point is repelling the south seeking and attracting the north seeking. The head is attracting the south seeking and repelling the north seeking. So what do? Do we change it or leave it the same?
Leave it the same.
We left it the same, okay? So we must have done the same thing last time. The north seeking was the what? The head, and the south seeking was the point. Okay, now we're going on a small field trip, okay? Within the building. We're going to take this compass. So who wants to be in charge of the compass? Somebody. Okay, you just did something. Somebody else. Charge of the compass. Anybody? We're going to go down the hall. Okay. All right. So let's everybody head out the door. We're not going to room 265. That no longer has a.
We need our stuff.
Second? No, bring your papers, but you can leave your stuff. Last one out, turn off the lights and close the door. Just so here we go.
You lied there. Video
Yeah,
sequence.
yeah. Hey, we got to show him some tomorrow morning.
Oh, dang.
What?
Huh?
Huh?
Yeah.
Ooh.
Now,
Yes.
what's that? Yeah. Well, it does really turn on where you're Now, okay. All right. Everybody back. Okay. Here's the Toyota Technical Education Network Electromagnetism Master. That's what this device is, this box of things. Okay? I plugged the black wire here into station 1 black wire and into our voltage generator, and the red into red. Okay, at station 1. Okay. What we're going to do is, and if someone would do this and record things, with the compass north needle. Now, you can't get too close to this because there's magnets all over the place here. Look at that. Yeah. All over the place here. Okay. So someone will be in charge of the magnet up here at the compass, and we'll see. So I need people to observe that as I do the deal down here. Okay? I'm going to, okay? All right. When I turn this on, see if any deflection happens to the compass needle. What happens? We're going closer to it, south seeking. What does it do? Repelled or attracted? Repelled from the which end of the coil? Yeah, which end? The right or left end? Left. Okay, so the south-seeking pole of the compass needle was repelled by the left end of the coil. Okay? What happens to the compass needle? South-seeking end of the compass needle was repelled by the left end of the coil. Now, why was that? I sent electric current through there. I didn't send any magnetism anywhere, did I? What's that? What is it that creates a magnetic field? Anyone know? Moving charges, exactly. I was moving charges through that and therefore made that a solenoid. Okay, with an end. So, which is the north pole of the coil? The left end or the right end? Right. What did it do? It repelled the south end, so that must have been the left end. Huh? Which one? The left. If it repels the south sequence, what repels the south? Huh? The right would be. Okay. Okay. You see, when I set juice through there, it repelled the south, meaning this must be the south end, because like poles repel each other. So that means the right end must be the north. Right? Okay. So that's C2, right? You got a C1 and C2, right? All right. What we're going to do is switch the polarity of the wire. Okay? So now the red's coming from the black, from the negative end, and black from the positive end. See if you see any change here. Yes. Now the south end is attracted to the south pole of the compass needle is attracted to the left end of the coil. Okay? Or you can just say yes, it was reversed. Okay? Which means the direction of current flow changes the polarity of the solenoid. Right? That then made the left end positive, the north seeking pole. Y'all can come look at this. You don't have to do it from a distance. Okay? You see when I reverse the wires, see how it attracts the south seeking? When I move the wires back. It repels the south seeking. See that? When it's red to red, repels. When I reverse the polarity, the left end attracts the south seeking. See it? So it reverses the polarity of your induced magnetic field. You reverse the direction of flow. Moving charges induce magnetic field, and if you reverse the flow, you reduce that. All right. So we're going to station B. Going to do red to red and black to black. Okay? I'll set it back up the way it was originally. Okay, no, not yet. Okay, we're going to do something else with this. Okay, I think we're through with the compass needles tonight. Okay, at station B, if y'all want to come up here and look at it, you certainly can. Station B, plug the wires according to the color, red to red, red to red, black to black, black to black. Okay? Okay? Now what I'm going to do, we're not going to do a 9-volt battery. I'm going to turn this up as high as it needs to be. Okay? And what we're going to do, we got two things to look at. One is red and green lights here. Okay? The second thing is this micro ammeter here. Okay? So, what I'm going to do is up the voltage to at least 9 volts. I may go, yeah, we're not going to mess with it. We're only worrying with this now, but it does. Wait. Let me see. Oh yeah, you're probably right.
That's what you wanted.
Well, I said you have your house, I go to my house.
Yeah. The micro ammeter connected.
I said go to the house.
Now, everybody come and look. I want to show you something. What our setup is here. What we're going to do is run some current through this coil. Okay? This coil is not connected to that coil. This coil is connected to the lights and to the ammeter. Right? So, we're going to see it running, doing things to this coil, making the changes happen here. They're not connected, but we're going to see if it works. Okay? Now, because the lights are hard to see,
Yeah.
I want somebody to go back and. Okay. All right. Now, I think y'all will be able to see the light, but then you're going to need to turn it on to see the ammeter, I think. Okay. You can see it?
Yeah.
Okay. Now, what I'm going to do here is crank this up to at least 9 volts, and it may not be enough, but we're going to try it. I think I've got Travis's.
Oh, that's
drifting.
the last one right there.
Yeah, I've got your drifting. You must have been in on this. Okay, it's about 9.7. Okay. Now what I'm going to do is connect and disconnect. When I connect, somebody's watching the lights and someone else is watching the ammeter. Okay? You ready? Ready?
Yeah.
Okay. Connect. Disconnect.
Light flash.
Okay, but it didn't when I connected. All right. Okay, let's crank it up a little bit more. That's 9.7. Let's go to 12. Okay. All right. Now look. Somebody look at the light. Someone else look at the ammeter. You ready? I can't see this whole here. Okay, here we go. Connect. Red light came on. And what happened to the ammeter?
I think I just leave it.
No, right. I've never turned the switch on this. Oh man.
We'll do that.
That's all right. I got it. Okay. Okay. Somebody's watching the lights. Someone's watching the ammeter. Connect. Jump which way? Positive? Okay. And which light? Red light flash. Okay, look at it again. I'm going to disconnect. Disconnect. Green light came on. It did nothing. Okay, look again. Okay, so you have to. Okay, this is going to be a connect. One person, some people look at the light, some people look at the connect. Red light, you got positive. Okay, I'll be looking while I disconnect. Disconnect. Okay, it did go negative. You have to see it right at disconnect and connect. Okay, and that was up to 12 volts. Okay. Okay, no, that's good enough. You don't want a prior wire. Okay, did everybody get that? Okay. Okay. Record what happens to the light and ammeter. Now wait, all you should be recording on number 4 is what happens on connection. Okay? Number 5 is what happens on disconnect.
Okay,
So number 4, what happened? Red light came on and ammeter jumped positive. Number 5, when they were disconnected, ammeter went negative, and how about the light? Green light came on. Okay? Now I'm going to reverse the electrodes again. Okay? All right, I'm going to crank back up to 12 or so. Okay, everybody watching?
All right, we'll wait.
Okay. All right. I reverse the polarity. So you tell me if somebody's watching both the lights and the ammeter, right? Okay. Connect. Green light. And the ammeter went negative. Okay. Tell me what happens on disconnect. Disconnect. Ammeter went positive. How about light?
I forgot to watch.
Okay. Okay. I'm going to connect again. Disconnect. Red light flash and ammeter went positive. Okay? That was a 12 plus volt. Okay, did everybody got enough light to write?
Yeah.
Okay, that was number 6. Hold the red on the negative electrode, black on the positive. What happens to the light and ammeter? When you connect, number 6. When you disconnect, on number 7. Okay.
Oh, we connect. Okay. I'm ready to see it.
Okay. Everybody following? Turn on lights if you need them. Okay. Okay. Did everybody get those done? Okay. Now, I want to remind y'all, some of you weren't looking at the lights or the ammeter until after they were connected. And when they were connected, all that current was flowing through there. But they weren't moving, were they? Ammeter wasn't moving, the lights weren't on. It only happened at connection and disconnection. Okay? So, Paul, could you explain those observations?
The different charges.
Say again?
The different charges.
Different?
Charges.
Okay. Yeah, and we reverse the charges, they change. But what's more, it's only, is everybody listening? Doesn't sound like it. Okay. It's only a changing magnetic field will induce the current in the second coil. Only the changing. It's only when it was connecting and going up or disconnecting and going down. That's the only time we saw current in the second plane. Only a changing magnetic field induces an electric current. That's why it was only on connection and disconnection, not when it was fully connected. All that charge is running through there, you got no current, no lights. Right? Only the changing magnetic field from the first coil created or induced a current in the second coil. When it was on full blast, 12 volts going through there, you didn't have it. It's only when you had a changing magnetic field in the first that you induce a current in the second. Okay. Now we're moving to station C. Okay. Now, Justin was over here playing with something before. Did you notice any difference in station C from station B? Okay. In other words, the coil is inside the other. This was beside the other. Okay? Hang on to that concept. Okay, what I'm going to do here at station C, I've got the colored wires according red to red, red to red. Oh, I don't do it. Okay. Yeah, we're putting use to the inside one and measuring the effect on the outside. They're not connected electrically. Okay? Now. All right. I'm going to start something greater than 1.5 volts. I'm not going to go anywhere close to 12. Okay? Well, this is actually, when this stops moving, it's about 1.7 volts. Okay? Turn off the light. Hold the phone. Okay? Y'all watching? Somebody watch light, somebody watch ammeter. You watching? Okay. Okay. Connect. Red light. It went negative.
Do it again.
Okay. Okay, let's get disconnect when I do it. Okay? Ready to disconnect? Somebody watching light, someone watching ammeter? Disconnect. No light. Okay, I probably need to turn it up. Okay, this is drifting all over the place here. Okay, where is my, oh.
You have that right touch for that one.
This is drifting all over the place. Okay.
I don't help any with that one.
Okay, I think your concept of touch may be right. Okay, let's go back down to around 2 or so. Okay, 2.6. Okay, I think it's steady. Okay, ready for the next? Okay, y'all watching? Connect. Red light.
What I told you.
What the ammeter do? Went positive. Okay, ready to read disconnect? Okay. Disconnect.
Green light.
Green light and
Ammeter went negative.
ammeter went negative. Okay. And that was with 2.8 volts. The other was 12.7 volts. Okay? Now, record the responses of lights and ammeter on both connecting and disconnecting. So on number 9, you put all 4 of those down there. Connecting, what the lights do, what the ammeter did. Disconnected, what the lights do, the ammeter did. Everybody get it, or you need it again? Say again? Yeah, red light came on. Green light came on. And what about the ammeter?
Ammeter went positive.
And negative when you disconnect. Okay, I'm going to reverse polarity again. I'm trying to bipolar myself here. Okay? And when you're ready, we're going to observe. Y'all want to observe? Okay? I'll leave it at the, now it's drifted up to 3. Okay? Okay, ready? Somebody watching the light, someone watching the ammeter? Okay, connect. Green light. It was negative. Okay. Watching to disconnect. Disconnect. And went positive. Okay. So again, everything reversed. Okay.
I don't know. Red light was,
No, I think on both of them. Red light was when it was positive and green light negative. Okay. You would have thought it was the other way, but it doesn't seem to be. Okay. You have a lab, don't you? Okay. All right. Now, that was number 10. And do connecting and disconnecting. Everybody got it?
Number 10, green light came on. Yeah. And went negative.
Okay. Does everybody have 10 done for both connecting and disconnecting light and ammeter? Right? All right. Now, I have a question for you. Those people watching the ammeter, was there a stronger response at station B, or was it a stronger response at station C?
C.
Stronger response at C. Even though we had more voltage at B, like 12, and less voltage, like 3 or 4, at station C. How can you explain that? What's that?
Because the power instead of going inside, it was going out.
What do you mean that?
Power you took in this core right here,
Okay.
went out. Inside.
Okay. You're getting right near it. Okay. Everybody listen up. Why were this is number 11. Why were the responses greater at C than at station B, even though B had much more voltage? And what Justin, I think, was trying to explain was that the coil that you were supplying the power to was inside the other coil. And what is it that determines what the response? The number of field lines being cut. And basically, all the field lines were being cut at station C, whereas at station B, they were end to end, just a few of them were being cut. So there's more field lines being cut at C than there were at B. Understood? Okay? More field lines being cut at C than at B. All right. We're going to turn off our power supply, disconnect everything. What's that? Yeah, turn on the light. Okay. What we're going to do now is move the yellow wires to station 8 and 14. They're already at 14. That's the ammeter. Okay. I think y'all need to come and look at this one. It's going to be hard to explain unless you look at it. Okay? At station L, that's where we are right here. Plug 2 sets of yellow wires to terminal 8 to 14. And one person should turn the coil clockwise, and the others read the ammeter. So here's the coil, turn it clockwise. That's the clock. What happens to the ammeter? Turn it faster and harder. It goes positive. Barely positive. Okay?
Please.
That's number 12.
So,
Yeah.
Oh, yeah.
Barely positive.
we say positive.
Huh?
Number 12 positive.
Yeah. Recorded response, it goes slightly positive. Okay? Everybody got it?
That's all.
You want to come see it? Or maybe everybody's word for it. Okay? Now turn it counterclockwise. Going after the ammeter. It goes negative. Okay? Second? I couldn't hear. Negative. It goes negative. Ammeter goes negative. Now what I'm going to do next is reverse the wires. Okay? Alright? Now repeat it, turning both directions. Okay, turn it clockwise. Second. Clockwise. Going negative, turn it counterclockwise. And it goes positive. So it's just reversed. Okay? Now, here's where you need to be looking at this to answer this question. So you need to be looking at this to answer the next question.
Number 14.
Number 14. Okay? We just reversed the wires and did that stuff, even though you didn't have a blank to put it in. You saw what happened. Okay. The question here is, what kind of connector do we have here? Notice, okay, there is absolutely no power going into this. And yet we were reading ammeters. Electricity coming out, current coming out, right? Even though there's no power going in. Now what we do have is a magnet up here, a magnet down here. So you have, and this is north, so the field lines are pointing like this. And when you turn the coil here, whichever way you turn it, you are cutting different numbers of field lines, just like we did back here. So there you'd be cutting the most field lines, there you'd be cutting the least field lines. And as you turn, you're changing the number of field lines being cut, right? And that's making only a positive charge. But look at the connector here. Can everybody see? Describe that connector. Here's an arm here, an arm there. And what do you have in between? There's a split there and a split there. Anyone want to make a guess of what they call this? You automotive people, if you ever worked on old cars? Second? No. It's more like the alternator.
Well, that's on every car.
I know, but the older ones had a special kind of alternator, as opposed to what they have today. It's called
They had
a
6 volt.
no, split ring commutator. Y'all heard that?
Nope.
As in class, you didn't hear it?
Nope.
When I talked about it in class, you didn't hear it?
Oh, yeah.
Oh, yes, you heard it. I thought so. Okay.
Split.
Split ring commutator. Huh? Split ring. This is number 14. The first little blank there, you have to write 3 words. Split ring commutator. And if you'll come, I'll sort of illustrate what I'm talking about here. Okay? Split ring commutator. Okay? Well, what's happening when I'm increasing the number of field lines being cut, as in going from this position to that position, increasing that in a certain direction, that would tend to go one way, and the current does go one way. But then when I go to switch, notice the contacts now touch the other piece. And when they do, rather than alternating current, like a generator does, it flips it back and makes it DC, direct current. And that's why you see it's not just a steady thing, it's sort of pulse DC. If you remember in class, the wave goes this, this, this. It's always positive. That's the split ring commutator. Okay? And turning the other way, it's always negative. Like that. So what's the result of this? A pulse direct current, pulse DC current. That's the second part of 14. Pulse DC current. DC current is actually redundant. It's direct current. Okay. Now, and notice how we did that. We had a fixed magnetic field, and we turned the coil, and that created a current. Okay? At station G, what we're going to do now is turn the magnet inside the coil. Okay? Someone's got to do that while someone else is looking at the ammeter. What do you notice?
When you go forward is when
He's playing with it. Okay. What do you notice about the ammeter?
I'm going farther to the left.
Isn't it going both directions?
It is.
It is. Okay.
I thought he was going back.
Well, he was. Okay. Yeah, it does the same thing, but that's because you're playing with it.
Yeah.
If you do it this way, you'll notice it is still going positive and negative. Okay, apply your
So it goes in both directions.
All right. At station G, connected to we did that. Record the responses of the ammeter. It goes both positive and negative. Are y'all listening? Okay. You got 15? Okay. You got it? Well, I answered it. Okay. Record the responses of the ammeter. What was it?
It goes both positive
And negative.
Yeah.
Okay? Now, what differences, this is 16, do you see from those at F that you didn't see at G? Or you saw it? Yes. At F, it was direct because it had a split ring commutator. At G, there's no split ring commutator there, so you have alternating current. Anytime you're changing the lines, field lines inside the coil. Now, here, you're changing because you're spinning the magnet. The coils are fixed. Okay? So when it's the south field changing, you send current in one direction, north sends it in the other. And that's why it alternates between positive and negative. You can actually see it better if you turn it more slowly. Okay? But you have no split ring commutator to make it go on the other direction. Okay? What's the feel? Is this worthwhile?
Oh yeah.
This was awesome,
What do you think about it?
What's that? Okay.
What do you think?
Nah, I'm gonna say both of y'all. Hey, can I have?
Okay. Who needed the previous lab? Okay. Anyway. Okay.
Oh, yeah. Oh, I need a load.
Yeah, me too.
Hey, what are you doing?
Okay. Is it just the one previous lab?
Yes, sir.
Okay. Now I had a stack of labs in my hand.
Is it okay?
Before I lose them. No, that's not them.
I got some papers.
Huh? Ah, here it is. Oh. I'll take
Some research paper and more.
all right. Does anyone need any of the previous labs? Okay. This is just the last. Okay. Here. Okay.
You turned the research paper in. You said these? Yes, you did.
Okay. Ohm's law. One. That's one. Ohm's law. Ohm's law. Ohm's law. Yep.
only got one game.
Oh, okay. Anyone else need on the wall?
Me, I do.
The source pad.
I do.
Okay, on the wall.
You gotta have two sources.
Okay, on the wall. Wall. Yeah, it's got it. Yeah, there you go, right there. Thank you.
I didn't take that test too.
All right, you test takers. Anyone else need to take the last test? Anyone else need on the wall?
It wasn't the last.
Now, the problem is I only have one on the wall left, and I have two people absent. Okay? Someone got two. Okay? Now I've got none left and two people absent. That's sort of suspicious. Let's see if they were here last time.
Yeah, I forgot what test I missed.
Okay. Yeah. Bailey got the last one. And Taff, I think, got it. So, yeah, we're probably okay. Okay. Now, you want the test. Okay, we're going to take in here. Yeah, I think I set it aside to give you. Yes. Okay. You can put my that on heat and temperature, or was it on energy? Okay. Let me see if I've got a score for you. That may be why. Yeah, you've already taken this one. It was the previous one, test 3.
Oh,
I'm sorry.
this one.
I bet you I've got an extra one of those. Whoa, maybe not. I don't know how I'm short that one. I know how I was short the other one because you had already taken it. But why am I missing one of these? And again, it may be what I was guessing before, that I set it aside, give to you, and I wound up having it somewhere else. So I'll be back in a few. Oh, it was test 2. No. Sorry to make you wait this long.
That's fine.
Make sure I have a score for you on that one. I have a score for you on that.
Yeah, I think I took this before.
Was it test 2? That
It was the one right before spring break.
must have been
The
test
one-
2.
Yeah, the one during.
I can't believe I did that. I didn't check this first. Did you already write something?
No, sir.
Okay.
That's what I was looking at.
Huh?
This looks familiar.
This is amazing. I should have checked that. Here. right here. I don't have to go make a copy. I should have known that was part of the deal. Okay. That's why I didn't have a copy of that either. Because you'd already taken it. And I've already returned it to you too. Okay, I think I have it. All right. We're working on that. I'm going. Oh, I've been